No, 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 no. Hello, hello, hello. No,
Hi, could everyone hear me?
Yes, I can hear you. Good morning.
Thanks. Just want to check, is Bharat here in the room?
Hey, give me a couple of minutes. Maybe we are experimenting problems with the audio. Just give me a sec.
Oh, okay, no problem.
Hello, hello.
Hi.
Maybe we can hear you.
I can hear you. Could you hear me?
Yes, but not in the room. Just give me a couple of minutes.
Sure.
Esta versión no me contó.
Mm.
Maybe
So
we
hi.
can hear you now.
Hi. Could you hear me now?
Yes, we can hear you.
Okay, good. I guess there are some kind of issues in the physical room too. Hi, Oscar. Just want to check. Is the issues in the room have been fixed? So just wondering. Just let me know when the things have been fixed, and I could start the workshop. Thanks.
Hello, can you hear me?
Yeah, I think I can hear you.
Okay, I think you also gave the. Yeah, I think we can start.
Okay, good. Thanks for help with the equipment issues. So okay, so let's get started. Sorry for the for technical issues. So hello everyone. So I'm Shu Chao. I'm Shu Chao Yao from Georgia Mason University. So I'm one of the program chair for our workshop AI Challenge IoT. So let me just have a quick introduction to make sure we can finish all this kind of logistics things before be- um, before 10:10. So first I want to say welcome to our workshop, internet workshop on challenges in artificial intelligence and machine learning for Internet of Things. So first, I would like to thank all the colleagues for their kind of support. So without them, we are not able to make these things happen. So for especially for the program community has reviewed multiple paper in a timely manner, and also for the steering committee that take the initiative to have this workshop, and also for we have another program chair. I'm not sure. I think Baraj has a conflict with another session. He may join us later, but Baraj is the other program chair has also done a lot of work to make the workshop happen. So thanks for all your efforts. And before we move into the technical session one, so another things to mention is as we mentioned in the call for paper in our workshop, so we are going to select a best paper award. So this year the best paper award is select from with the so basically the steering committee goes through all the paper we have accepted and picked one they found it is most innovative in the idea, so and select as a best paper award, as you can see. So this year best paper award is the AI assistant cell level for detection and localization in solar PV electrical luminous image. So what's having the comment given by the steering committee is that so this paper focuses on a relatively new problem domain, and it represents a non-trivial pipeline to detect and localize the fuzzy solar panels, which can be useful in practice, and the methodology may be also practical to other problems. So let's congratulate Ahan and his colleague for their nice work. So I think that's all for a kind of very brief summary. Sorry, that's for a very brief opening and introduction. So I think we can move directly to the technical session one. And so just want to check Vinod is here. So if he's here in the room, okay. Okay, let me introduce Vinod. Vinod Nagar is a PhD student in VU Amsterdam. His research focus is on design and implementation of efficient system for video stream analytics, especially at the edge of the network. So let's welcome Vinod for his presentation. So by the way, I want to mention at the beginning that each, as you can see in the agenda, each presentation have 20 minutes, including Q&A.
Can you hear me now? Hello.
Yes, I can hear you.
Okay. Yeah. All right. Let's get started. My name is Vinod Nigre, and I'm from VU University, Amsterdam. I'm a PhD student there. And today I'm going to present our paper on timely edge video analytics. And I'm mostly going to cover
sorry for interruption, but
this work was done together with the master student Raymond Wilder and with my supervisors, Professor Henry Ball and Dr. Lin Wang. So here is the outline. So I'm going to cover motivation for timely edge video analytics. And then we are going to see some of the challenges in realizing timeliness guarantees, especially in the edge environment. And then we are going to discuss some of the state-of-the-art systems, like see the classification of those systems. And then we are going to discuss about our simpler approach, which is based on the feedback control to guarantee the timeliness. And then we'll conclude with some future work. So let's get started. So, okay. So as we know, nowadays modern intelligent applications okay, so nowadays modern applications such as augmented reality, autonomous driving, or traffic monitoring, they use neural networks for accurate analysis, right? These neural networks, they are, especially the accurate ones, they are bigger in size, and therefore they are computationally and memory-wise quite expensive. Therefore, their deployment on resource-constrained edge devices, such as mobile phones or drones, is quite challenging. And also, we know that edge computing, that is provisioning resources near the edge of the network, seems to be a viable solution, right, to deploy these modern applications. But the question is, does edge computing really solves the problem, right, that is deploying intelligent applications near the mobile or IoT devices? Well, to some extent it does, but there are some challenges to it, and we'll cover that in later slides. So first, user interactive or mission critical applications, they need accurate results to be delivered on time. Otherwise, it could be bad for end users in terms of user safety or user experience, right? And also, these mobile or IoT devices, they typically use wireless medium such as the Wi-Fi network or the LTE network for communication. And these networks are highly dynamic, and we'll see what that means in the next slides. And also, if you want to offer an analytic service near the edge, it is important to define latency, SLO, in an end-to-end manner. Not just the processing time on the server side, which has been a traditional definition in cloud computing. So the latency SLO should include the network transmission time also. So when designing a system, not just the accuracy metric, but also the per frame latency SLO, that is the timeliness should be considered. And that was about the needs of applications, right? Now let's see what are the challenges in realizing timeliness guarantees. So here we cover around 4 challenges. The first one is network variability. As we said before, these end devices, they use wireless networks, which are highly dynamic in terms of bandwidth values. Yeah, the reasons could be like environmental interference or end user mobility and so on, right? Here in this graph, we can see that the bandwidth, here we show the bandwidth values in a Wi-Fi network when user is moving around. And we can see that the bandwidth values change quite frequently and dramatically. And also the peak to value ratio is around 5x. So in such a dynamic network, actually can bring or introduce a great variability in network transmission time, which leaves the variable budget on the server side to do the inference. Another challenge we can think of is the performance volatility in the edge platform. So although edge resources are relatively powerful, but they are limited and static. So we might have to share them with multiple applications or users, right? And sharing resources, that is co-locating jobs together, might introduce the performance interference, and that can affect your inference timings, right? Might bring the variability in the inference. So here is one experiment which was reported in the paper named Allen. And we can see that depending on the task and also on the compute resource type, the inference timing can vary with the degree of co-location. So here the left figure actually shows time variance with co-located jobs, without co-located jobs, sorry. And the right figure shows the time variance with co-located jobs. And we can see that the median latency and also the variance, it increases with the co-location. So without the proper isolation, performance isolation mechanism, it will be hard to avoid the interference and to get and then get a stable or predictable performance, which is generally needed in timeliness guarantees. The next challenge is the cascading or the queuing effect. So in a typical video analytics pipeline, we have buffers before each of the components. Right? For example, before network transmission module, we have a buffer to hold pending requests, right? And if we make a decision for the current request, that decision might actually have an impact on the future frames, right? In a complex way. So this cascading effect can also introduce a variability in your timeliness guarantees. Last but not least, the challenge is tag-based DNN inference. So many existing systems, they assume applications with single DNN, right? But there are applications like automated license plate recognition, which might use a cascade of DNNs or graphs of DNN to do the processing. And such a, do the tag-based inference, we need to actually have a proper scheduling and coordination among different DNNs, right? And we also have to think about the cascading effect that we discussed before. So this tag-based DNA inference also introduces the complexity to the timeliness. So that was about the challenges of timeliness guarantees. Now let's see the status of existing systems. So here we can broadly classify the existing video analytics system in two categories: the adaptive systems and then the DNN inference server. And then we check whether these systems actually handle the network issue or the server side compute management or tag-based inference or per frame latency SLO. And we see that in video analytics, in adaptive analytics, it conducts the trade-off between accuracy and resource consumption, right? Yeah, and generally the per frame latency SLO is rarely considered or ignored completely, and mostly the trade-off is conducted by adjusting the application-specific knobs like frame rate and frame resolution, for example. Right. So on the other hand, we have these DNN inference serving systems. So mainly the goal here is the resource and DNN management on the server side. But there are many, there are some of existing systems which actually guarantees per frame latency SLO, but that is also mostly on the server side, similar to the cloud serving systems, right? And they do not consider the client network conditions, and therefore they might fail to deliver your results on time. So that was about some of the challenges in realizing the timeliness guarantees and a bird view of existing systems. Now let's see our preliminary design, what we want to propose. So specifically, we leverage a reactive controller that looks at the history of past outcomes of our adaptation decisions and then guides the system towards its target. Some of the benefits of reactive controller is we did not have to worry about, we did not have to actually probe bandwidth conditions or explicitly design performance model of this complex system. Right? Here, in this case, we simply consider this entire system, including the network and server, as a black box. Right? And specifically, what we do is we have this controller on end device which adjusts the frame sizes according to the feedback that we receive for the early, according to the feedback that we receive for earlier frames, right? And on the server side, what we do is we select DNNs whose input size actually matches with the frame size. So therefore, we need to deploy a pool of DNNs that has that have various input sizes to adjust to our adaptation decisions. And one of the goals in our design was to be lightweight in terms of compute, memory, and network. So in more detail, here is a simpler proof of concept reactive controller, and we can use much more sophisticated controllers like PIDs, which has some theoretical guarantees, but we consider that as a future work. So here the state manager, it basically maintains the history of past outcomes. Specifically, what it does is it measures the end-to-end latency per frame, and then it computes the deviation of it computes the deviation from the target, and then it computes this error term, which is just a scaled version of this deviation to penalize, for example, missed frames more heavily than the early received frames, right? And then it maintains this history of past error terms and computes the moving average to indicate the current state of information. And this current state of information is then fed to the controller, and the controller internally uses a threshold-based approach to decide whether to upgrade or downgrade the frame sizes. And specifically, we use additive increase and multiplicative decrease policy to make our adaptation decisions, and which can be conservative when system state degrades. Right. So that was about our simpler proof of concept controller, reactive controller. Now let's see how it performs on a real bandwidth trace. Right. Here, the top figure is the bandwidth values that we see on end devices. And also specifically what we do is we replay video at 30 frames per second and set the latency deadline of around 33 milliseconds, which is quite time. And here we see in the middle row, the controller actually chooses smaller frame sizes as the bandwidth values drop, and it improves the frame size as the bandwidth values improve. Also, the server on the server side, it correctly chooses the DNN, which actually matches its input size with the frame size selected by the controller. Right. Here we see that the end-to-end latency of 98% of frames is within the latency deadline of the SLO. Right. So which makes the simpler approach quite effective. And if you look at the CDF, right? So in the CDF, we see that the median latency is around 29 milliseconds, which is quite close to our target deadline. And yeah, so that indicates it's not that conservative, right? But of course, it depends on controller parameters that we choose. So, okay, that was about our simpler proof of concept reactive controller for timeliness guarantee. We proposed an adaptation mechanism where we adjust the frame sizes based on feedback control. And yeah, if you want to deploy this approach on a wider scope, there are some limitations, and we highlight here a couple of limitations. The first one is feedback control is less sensitive to rapid changes. Yeah, so but if on the other hand, if we have a highly responsive adaptation algorithms, then the server has to switch between the DNNs quite frequently to adjust to our adaptation frame size adaptation, right? And that might incur a huge cost. And also, if you want to support multiple clients or users or applications, then we need to properly select DNNs. It has to be optimal, and also the scheduling needs to be considered with their optimal batch sizes, right, to improve the efficiency, which is challenging and non-trivial. We therefore, as a next step, aim to implement a modern serving system that jointly considers the client network conditions and DNN management on the edge server. So that was about our case for timeliness guarantees in the edge environment, and I thank you for listening, and I'm happy to take questions if there are any. Thank you.
Thank you, Vina, for your presentation. So, any question? Do you have any question for the presentation? If you have a question and join remotely, you can just open your mic and say it. Okay, I think I have a question for Navas. So I think this is a very interesting work. So I think one thing you have mentioned in the presentation is that you also would like to take the kind of the relationship between a very complex video analytics query into consideration to adding to a DAG and to putting to as a factor to do the optimization. So is that something that can be handled by our current framework, or it is a more like a future work to be considered?
So you are not very audible here, but if I understand your question correctly, you're asking me if we actually consider the tag based in the experiments.
Yeah.
Hello.
Yeah. Yes.
Yeah. So at the moment, we did experiment with a single DNN, but as I said, like we treat the entire tag or the entire system as a black box. So we actually hope to see somewhat similar result in a tag-based DNN inference serving, and yeah, because the feedback actually would cover the issues that we see in a tag-based approach, but of course it also depends on how the server schedules these DNNs. But yeah, in this work we simply assumed a single DNN per application. But yeah, definitely we are going to consider tag-based as a future work.
Thanks. Sounds interesting. Okay, let's thank the speaker again. And we have our next paper. So characterizing the role of a preprocessing parameter in audio-based embedded machine learning. So our presenter, Vivek Tuzan, is purchasing her PhD in Trustworthy Edge Intelligence at Delft University of Technology. She received her master in computer science from the University of Cape Town. Prior to starting her PhD, Vivek worked as a data scientist and business analytic in the energy and e-commercial sectors. So let's welcome Vivek.
Thanks so much. I'm just quickly getting my presentation up. Great, good morning. Thanks so much. My name is Vivek Tuzan. As already introduced by Shao, I am a PhD candidate at Delft University of Technology, and I am presenting work that I did with my co-authors Akil Mathur, Fahim Kausa, and Aaron Deng while doing an internship at Nokia Bell Labs over the summer. I'll be starting with motivation of the work. Introduce a research question and approach. I'll then give an overview of sources of bias in embedded machine learning and speak about quantifying fairness in embedded machine learning. And then I'll move on to a case study that we did in audio keyword spotting. I'll present our empirical results and finally round off with future work and conclusions. I want to start with 3 use cases of AI in today's consumer devices: audio keyword spotting and smart speakers, face recognition and smart cameras, and heart rate detection with optical sensors and smartwatches. These applications have become possible due to technical advances in embedded machine learning. Embedded machine learning is concerned with porting and deploying machine learning models to embedded devices and running them directly on device. A major advantage of this and a motivation for embedded machine learning is privacy. If sensor data is processed on the same device that collected it, then sensitive user data does not need to be sent to centralized storage and processing facilities in the cloud. And yeah, so that is a real advantage. At the same time, computing and energy resources of embedded devices are limited. And so the gain in privacy does not come for free. So increasing research efforts and engineering are really devoted to improving accuracy and system efficiency of embedded machine learning systems. Meanwhile, off-device, the AI powering popular embedded machine learning applications like audio keyword spotting, face recognition, and heart rate detection is under scrutiny for being biased. This can mean that the system discriminates against accents, that it does not recognize faces, or that it fails to accurately predict heart rate for darker skin tones. As researchers working on intelligent devices, bias and discrimination directly impact the usability of the products that we develop. So traditionally, machine learning is primarily concerned with with algorithmic accuracy, which is an average measure of performance. As already mentioned, in embedded machine learning, system efficiency is an additional important metric, as latency and energy consumption pose hard constraints. We now add fairness as a third metric to consider, as user-centric devices must work reliably for all users. This intersection of these three objectives has motivated the research question that we have investigated in this paper. How can we balance accuracy, fairness, and system-based performance metrics in embedded machine learning under varying deployment conditions? There are several challenges to overcome when considering bias in embedded machine learning. Firstly, fairness has not been quantified and thus can't be measured. Then, where the cloud offers machine learning limitless compute, embedded machine learning needs to balance fairness and accuracy metrics with system efficiency, like latency and energy consumption. And finally, when deploying embedded machine learning across thousands or millions of heterogeneous devices operating in unpredictable contexts, input data is likely to diverge dramatically from training data and assumptions. We approached the research question in 3 steps. First, we mapped sources of bias that arise in embedded machine learning systems. Next, we quantified fairness in embedded machine learning. And lastly, we conducted an empirical analysis to characterize fairness trade-offs in a case study. I'll give a short primer on fairness in machine learning. Fairness can be considered as the absence of any prejudice or favoritism toward an individual or group based on their inherent or acquired characteristics. Bias, then, is a source of unfairness. Indeed, many different forms of biases exist in the machine learning process, such as data collection, sampling, and measurement biases. Many recent studies have revealed evidence of bias in machine learning applications, ranging from gender classification, recruitment, and natural language processing to automatic video captioning and COVID-19 policy development. Finally, discrimination is the source of unfairness due to human prejudice and stereotyping based on sensitive or protected attributes. It's important to add that in many countries, discrimination carries legal consequences and is something that engineers and developers should be taking seriously. I can hear somebody's background noise. I'm just wondering. Thank you. Okay. It is a misconception that bias in machine learning is merely a problem of balancing training data. In reality, especially in smart products, bias creates feedback loops and emerges at different stages during a smart device lifecycle. Machine learning starts with data. This means that historical and social biases, for example, choices made during data labeling, are encoded by algorithms into machine learning models. This can be thought of as a data to algorithm bias. The algorithm is then used to make predictions that are presented to users. The predictions, however, are not neutral and create algorithm to user biases, like ranking bias, where search results ranked higher are deemed more relevant. Then users interact with the results, which generates more data, which is fed into algorithms. And after some time, in the case of search, results that get more clicks are ranked higher, get more clicks are ranked higher, and you get the idea. So one of the framings that's been used to look at specifically the data to algorithm bias is to look at these biases in terms of where they arise. So in the development workflow, during pre-processing, in-processing, or post-processing. We've drawn inspiration from this existing work on bias in machine learning and have categorized sources of bias arising out of design choices during pre-processing, in-processing, and post-processing in embedded machine learning workflows. With bias and discrimination being known weaknesses of machine learning systems, it's a matter of both importance and urgency to investigate their prevalence in the rising trend of embedded machine learning. So this work is one of the first, if not the first, research that considers fairness alongside accuracy and system efficiency in embedded machine learning settings. We deal specifically with design choices during pre-processing, namely the role of pre-processing parameters. So next, I will look at sources of bias in embedded machine learning systems. In synopsis, in embedded machine learning, we train a model to be used for inference under particular hardware and deployment constraints. This is done through interventions like compression or resampling, applied before, during, or after training. It is well established that training conditions like the dataset, algorithm, and hyperparameters, as well as deployment constraints such as dataset shift, affect inference accuracy. We broaden our perspective on deployment constraints to include aspects such as hardware sensor limitations, which are often overlooked. Furthermore, we position that these constraints not only affect accuracy, but also fairness. The interventions in the embedded machine learning workflow can overcome these deployment constraints. However, this comes at a cost to accuracy, and we hypothesize also to fairness. I've colored those aspects of the embedded machine learning workflow that we have studied in this paper, in this slide, to make it easy to put it all together. Now I present a quantification of fairness. We consider a model fair for a subgroup of users if the subgroup's individual accuracy score equals the model's average accuracy score across all subgroups. So if the model produces an accuracy score of 0.8 for male speakers and an accuracy score of 0.8 for all speakers, then the model is fair for male speakers. To operationalize this metric, we set up requirements and validity constraints. Our metric should penalize favoritism and prejudice equally, score models as being more or less fair, and consider positive and negative prediction outcomes. We assume that all subgroups are equally important in the application context and that fairness is independent of subgroup size. Subgroup contributions to model fairness are thus not weighted. Importantly, ground truth labels are exactly known and undisputed, so that there is no risk of label bias. Moving from the conceptual to the empirical, we set up a case study with rigorous experiments in the embedded audio keyword spotting domain. An audio keyword spotting system takes a speech signal as input and pre-processes it to generate input features. Pre-processing involves selecting a frame length and frame step, a window type, feature types like log-mil spectrograms or MFCCs, and feature type dimensions. The output of the pre-processing step is a set of input features on which a neural network model is then trained for classification. I will be speaking a lot about pre-processing parameters, and thus want to give a bit of a background about what they are and how they are selected. Pre-processing parameters are a set of normative design choices. Their selection is based on several decades of empirical traditions in the speech recognition domain. Across study, we've seen little variation in reported choice of pre-processing parameters. While it is possible that authors conduct experiments across a variety of settings, this is typically not reported, and papers focus solely on algorithmic design and evaluation. Rather than focusing on algorithm design, we take a data-centric approach and investigate how different pre-processing parameters affect holistic model performance under varying deployment conditions. Here you see spectrogram images for the same two keywords, stop and no, at 16 kilohertz sample rate on the left-hand side and at 8 kilohertz sample rate on the right. In the top images, the y-axis represents frequencies on a log scale, while in the bottom images, the y-axis has been transformed to the MEL scale, which is a coarser scale designed to accentuate the range of human hearing, and it's popular in speech recognition. It is easy to see that the image representations in the four scenarios are not identical. Considering that audio keyword spotting relies on image processing algorithms, it is justified to consider the effect of pre-processing parameters, like log-mil spectrogram features, under varying deployment conditions, like sample rates. In our analysis, we consider fairness for user subgroups based on speaker sex, which is the biological and physical distinction between male and female speakers. In voice-related applications, this biological difference is important because of the physiology of male and female bodies that affect voice. The objective of our experiments is then to characterize the effect of pre-processing parameters on the overall embedded machine learning performance for an audio keyword spotting task under varying deployment conditions. The pre-processing parameters we considered affect the dimensionality and volume of the data input, and thus directly impact resource requirements and system efficiency. We consider the effect on sample rate as a deployment constraint. While architectures are typically trained at 16 kilohertz audio input, in reality, many devices only sample audio at 8 kilohertz. Moreover, as pre-trained architectures are frequently used as black box predictors, we wanted to study the effect of sample rate divergence. That is, if an 8 kilohertz data input is unknowingly provided to a model trained on 16 kilohertz and vice versa. Finally, we trained 2 neural network architectures on a well-known benchmark dataset of audio keywords that we labeled and equally weighted for male and female speakers. I now move on to the analysis of our experimental results. Firstly, pre-processing parameters matter and are a normative design choice. Here we see that for models trained at 16 kilohertz, feature type and feature dimensions, frame length and frame step can be selected to favor system efficiency, accuracy, or fairness. Taking a look at this visually, here I show the impact of the feature dimension parameter, specifically the number of MEL frequency bins on the distribution of accuracy scores of 2 model architectures trained with 16 kilohertz data using log-MEL spectrograms as feature input. The bin sizes are arranged in order from 20 blue bins at the top to 80 brown bins at the bottom. It is easy to see that model accuracy is greater for fewer bins, and that this effect is greater for the smaller low latency CNN model at the bottom than the larger CNN model at the top. Similarly, we can look at the effect of feature type on accuracy, where we see that both log-MEL spectrograms and MFCCs perform similarly well for the CNN architecture at the top, but MFCCs on average perform better for the low latency CNNs at the bottom. We also found that while some parameter settings, like choosing fewer feature dimensions, support better outcomes across metrics, others, like frame step, present a trade-off. A longer frame step is better for system efficiency, while a shorter frame step is better for accuracy. Embedded machine learning developers can use these insights to select pre-processing parameters that let them balance accuracy, fairness, and system metrics based on application requirements. This insight strengthens the data-centric approach to embedded machine learning that looks at the entire machine learning workflow rather than focusing purely on algorithms to improve accuracy, fairness, and system efficiency. Our second insight is that the choice of pre-processing parameters is sensitive to deployment conditions. Here we contrast the optimal parameter choice between low latency architectures trained at 8 kilohertz and 16 kilohertz. At the lower 8 kilohertz sample rate, choosing MFCCs as feature type will result in models with better accuracy, while choosing log-MEL spectrograms will result in models with better fairness. We did not include a closer fairness analysis in the paper, but when examining models more closely by looking at accuracy for male speakers here on the x-axis and for female speakers here on the y-axis, we were surprised to see that the feature type plays a deciding factor on whether models perform well for male or female speakers. Blue dots are experiments that use log-MEL spectrogram features, while orange dots use MFCCs. The black diagonal indicates equal performance for male and female speakers. For 16 kilohertz data, log-MEL spectrograms perform better for female speakers and better overall, while MFCCs tend to perform better for male speakers. At 8 kilohertz, however, there's a clear separation between experiments with log-MEL spectrograms and those with MFCCs, indicating a potential trade-off in models that work well for male speakers versus those that work well for females. And finally, let's consider sample rate divergence. On the left, we show again the recommended pre-processing parameters for low latency CNN models trained on 8 kilohertz data input. When the input data for inference is sampled at 16 kilohertz, diverging from the training sample rate of 8 kilohertz, the only important consideration for good accuracy and fairness is that log-MEL spectrograms are used as feature types. Such kind of sample rate divergence are not far-fetched. In typical embedded machine learning settings, which pre-trained models are downloaded and reused, they can easily occur in real-life workflows. So our third key insight is that choosing the right pre-processing parameters can help create embedded machine learning pipelines that are more robust in unknown deployment conditions. And just a a quick view is that a perspective, we found this fragility of audio models to sample rate quite surprising, especially when looking at the image input at 16 kilohertz and 8 kilohertz. It appears a bit like, it doesn't appear like such a great difference in the spectrograms, and it's surprising that it can result in such a significant drop in accuracy, and especially a significant difference between the accuracy performance of MFCC and lot-mel spectrogram features. I'll skip this slide. Yeah, and so finally in this paper, we present a first exploratory characterization of the effect of pre-processing parameters on 3 embedded machine learning metrics. In future work, we will do an in-depth analysis of fairness challenges and approaches for mitigating bias. We will expand the study to other tasks and datasets to establish consistency across parameter choices. And finally, we're working on investigating other aspects of the embedded machine learning workflow for bias, fairness, and efficiency, namely compression and context shift. So the key contributions in summary is that we've shown that seemingly innocuous pre-processing parameters like feature type, feature dimensions, frame length, and frame step can create havoc in real-life embedded machine learning deployments, affecting not only accuracy, but also model fairness. We provided guidance on pre-processing parameter selection to balance accuracy, fairness, and system efficiency metrics. And as a whole, we present a first study on fairness in embedded machine learning. The one important message to take away is that embedded machine learning systems need to consider fairness as well as accuracy and hardware system constraints to account for heterogeneous deployment conditions and diverse end users. Thank you.
Thanks, Vivek, for the presentation. So any question? Okay, so I think since we are out of it of the time schedule, so let's just move directly to the next paper. But if you have any question to the paper have been presented, please welcome to use the Slack channel to ask question, and I think also can do the reply on the channel as well. So okay, let's move to the third paper. So third paper. Vision paper towards software-defined video and analytics with cross-camera collaboration. So the presenter is Junhen Ying. Junhen Ying is a PhD student at the Department of Computer Science and Engineer at Seoul National University, Korea. His research interests including mixed reality and mobile edge AI. He is currently working as a research intern at Nokia Bell Labs, Cambridge, working on video and analytics. In this talk, he will be presenting his ongoing work for his internship. Let's welcome Junhen Ying for his presentation.
Thank you for the introduction. My screen sharing is working well, right? Thank you. Right, so hi guys, good morning. I'm Juhan, as introduced, and today I'll be introducing our work. And actually, this is a vision paper, a position paper that actually summarizes our research vision and potential research ideas that we are currently investigating. The title is Towards Software-Defined Video Analytics with Cross-Camera Collaboration. All right, so as you all know, cameras and video analytics are becoming increasingly pervasive in our lives. There are increasingly many cameras deployed worldwide, and with the recent advancement of AI, video analytics are increasingly deployed and becoming more ubiquitous in our lives. And actually, in these kind of environments, we are envisioning a case where multiple video analytics apps are concurrently running over the same place with multiple cameras deployed. So let me just give you an example scenario. So first of all, imagine a case where there are multiple cameras installed in the highway, and there is like one service provider that monitors the traffic and gives you an update on how many traffic there are. And there can be another application run by the police officers to track the crime suspect vehicles and so on. Thinking about another scenario, there can be a lot of cameras deployed in a shopping mall, which can be used to monitor the users. For example, we can analyze the demographics of the customers, like, for example, the age and the gender and so on, to analyze like what kind of people visit the store more often and provide necessary services. And a security manager can use the cameras to detect shoplifting activities and track the suspects and so on. Yeah, so actually there are many, with these kind of like many cameras deployed, there are many applications currently running. But actually, we are seeing that current video analytics systems are actually quite limited in providing, supporting these kind of like environments. Yeah, so current practice is that there is one app developer that, so he deploys his own cameras, and yeah, he just uses his camera to, and deploys his, the AI models to provide his service. There's another app developer that also deploys his own cameras and necessary AI pipelines and so on. And actually, with these kind of like current practices, we think we are envisioning, have identified that these kind of practices have several limitations. So first of all, the camera deployment itself is very isolated, meaning that every app developer just deploys his own camera, and he has a privileged access to it, and other people cannot access them. So actually, there are many cameras, but only a partial set of cameras can be accessible only by the owner. And actually, in terms of the functionalities, the applications are very hard coded, and actually, it is very difficult to modify functionalities for other purposes. And also, in terms of the workload, there have been a lot of video analytics systems designed, but they have mostly considered a very simple stateless applications, for example, frame-wise object detections. So actually, we need more system support for diverse types of application workloads and so on. And also, like there's many cameras, and actually they have a lot of overlapping views, and there are many chances for collaborations and so on. But currently, they are all existing systems are all focused on just processing the individual cameras in an independent manner. And actually, the processing is mostly assumed as an architecture where the video streams are streamed to the central server, and just processed. Everything is done at the server side, and those cameras are just acting as a dumb streaming only devices. Yeah, so actually our vision is that emerging video analytics should be software defined, and actually meaning that these cameras need to be managed as a unified platform where every app developer can freely access them, and actually he can specify his whatever service he wants in a very flexible manner and utilize the platform to get the analyzed results and so on. Yeah, so this slide just summarizes the limitations of current systems and our vision. So summarizing, we are envisioning an environment where the cameras are managed as a unified platform. And on top of that, the functionalities are software defined, meaning that the app developers can freely configure the services running on top of the platform. And actually, as a benefit of the camera, these kind of multiple cameras managed as a unified platform, there's a lot of chance for these kind of cross-camera collaborations over overlapping cameras. I'll be dealing with that in a few more slides. And finally, in terms of the processing, we are not just assuming a dumb streaming only cameras, but smart cameras and edge cloud servers which cooperatively process the workload. Yeah, and actually to realize these kind of software-defined video analytics, we are envisioning that these kind of platforms should have support these 4 requirements. So first of all, so these kind of video analytics pipelines are commonly composed of multi-stage, multi-DNN pipeline running on multiple camera streams. So the system should be efficient enough to select the adequate cameras and adaptively adjust the pipelines to manage the resources. And obviously, there are multiple apps concurrently running, so the system should efficiently coordinate them. And in terms of the execution, it should utilize the heterogeneous smart cameras and edge cloud server to cooperatively process the workload. And finally, it should efficiently utilize the multiple cameras in a collaborative manner to improve the system efficiencies. For example, so you can utilize the overlapping views to minimize the computation, or you can also utilize the overlapping views to give diversity and improve the model accuracies and so on. Yeah, so yeah, this is just an initial version of the platform that we are currently envisioning. So there are multiple layers to support these kind of like software-defined video analytics. So first of all, there is a abstraction layer and the interface layer, which takes in the queries from the users and translates them into the actual workload. And given that workload, there is a quality-aware camera selector that selects the necessary cameras in the pipelines. And given like multiple application, the workloads from multiple applications, it utilizes the multiple edges to and orchestrates their execution in a holistic manner and so on. And actually, we're envisioning that while there has been a lot of works on these video analytics, they do not fully solve these kind of like all these challenges. For example, in terms of the query abstraction as APIs, these existing video analytics have mostly considered like frame-wise single-shot tasks like object detection and so on. So there has not been much work on abstracting this like video analytics workload, and there are so they some work they do, but they lack the expressibility for diverse SLO specifications and so on. And in terms of the camera selection and collaboration, existing works mostly assume independent processing of the camera streams, or assumes a very like static collaboration policy for a single app scenario. And finally, for the resource scheduling, so yeah, most of the prior works consider like centralized processing at the server, and in case they assume like these kind of like distributed processing architectures, they mostly focus either on the compute or the network latency aspect, and there's not much work that considers the end-to-end resource scheduling in a holistic manner. So actually, we are working on a project to deal with these kind of challenges, and in this talk, I'll be just talking about the latter two components, which mostly focuses on the system optimization part. Okay, so the first component is actually what we named the quality-aware multi-camera selector. So the goal of this layer is to select the camera streams and their pipelines for optimal resource accuracy trade-off. And actually, why do we need to do this? So actually, so this figure just illustrates like one example of a pipeline where we track these multiple query images from multiple video streams recording the intersection of a road. So basically how it works is that given the query images for each camera, we detect the vehicles, and for each detected vehicles, we run the vehicle identification network to track the vehicles. And after the queries have been tracked, we run additional feature extraction models to analyze their features and so on. And these kind of like pipeline is repeated for all the cameras deployed. And actually, there are many challenges for running these pipelines. So the first challenge is the computational complexity. So this is just our initial measurements. So as we can see here, so basically this pipeline requires a repetitive execution of multiple deep learning models over like multiple cameras. And actually our analysis is showing that with just 2 camera video streams, it already saturates the server GPU. So there's a lot of computational complexity. And actually for the feature extraction part, so basically there are many cameras capturing the targets. And basically depending on how the target is captured, there's a lot of quality variations. And actually, so yeah, using which camera stream to use, like determining that is also a very non-trivial and important issue. Yeah, so we are investigating some techniques to tackle the challenge. So the first idea that we're exploring is the cross-camera spatial temporal filtering technique. So basically the key idea here is that basically multiple cameras, they are deployed in the same environment, and they can have a spatial temporal correlation on their content. So why don't we utilize them to optimize the systems, so system resources and execution. Yeah, so yeah, just an example. So this black vehicle is detected in multiple camera streams. From this, we can learn the spatial correlation to identify redundant regions. And also within even the same cameras, there is a lot of temporal correlation, which you can utilize to remove redundant executions. We have actually, we are investigating these techniques, and we just did a preliminary experiment on this state-of-the-art NVIDIA AI City Challenge dataset, and we have seen that these techniques are, these spatial temporal correlations are quite effective in optimizing system resources. And also we are exploring these kind of like camera selection problem that adaptively selects the camera that captures the target with the highest quality. Actually, this is just an initial idea, and actually we are just in a process of working on this idea. But basically what we're trying to do is that when the same target vehicle, the same target is captured on multiple cameras, and actually over time, the quality in which the target is captured can fluctuate over time. So actually, why don't we select the best camera adaptively over time so that the analysis results can be very optimal. Yeah. Okay, so yeah, these kind of issues we are investigating. And also the second the component. So actually, when there's these kind of like multiple pipelines going on, why don't we utilize these like multiple edges and central cloud edge server to maximize throughput and satisfy the SLOs and so on. Yeah, actually the challenges here are that so basically the number of concurrent applications running, they fluctuate over time, and also the workload complexity can fluctuate over time in camera depending on the scene content. And we should jointly consider these kind of like heterogeneous computing powers of the smart cameras and the edge servers. And we should also consider the networking and energy overhead while balancing these workloads. So actually, we are designing these kind of like holistic resource orchestrator. And just to name a very few techniques. First of all, we are considering these like multi-edge workload balancing technique, which jointly considers these kind of like computing powers of the smart cameras, which can just range from a simple embedded device to a relatively strong embedded device with embedded GPUs. We also aim to consider these kind of like energy, the amount of energy theft, and the network bandwidth, in a holistic manner to like balance these kind of like workloads to maximize the overall throughputs. And also when there's like multiple applications concurrently running, for example, when the application needs to track multiple vehicles with different latency and accuracy SLOs, how to allocate resources and the execution order to satisfy the overall SLOs. We are also investigating these kind of ideas as well. Okay, so and actually we are in a very early stage, so stay tuned for our more results, which we would like to present in our future works. All right, so let me summarize this talk. So basically the cameras and video analytics are becoming very pervasive, but current video analytics systems are very limited, and we are envisioning a software-defined video analytics platform to cover like very diverse aspects of our future systems and so on. So I think that's it for today. And I would be very happy to take any comments and on our work, which would be very helpful in progressing our future investigations. Thank you.
Thanks for the presentation. So do you have any question? Okay, so I think I have a quick question from my side. So what we say about the camera quality, do you specifically mean that it is it is the resolution. So is it resolution is all the matrix set? You say it as a quality all. So if it's not, could you maybe give another example? What kind of the factor in the camera can have a strong impact on the quality in practice?
That's a very short question, and I really want to thank you for the question. So quality, yeah. How to define the quality? So that is a very important issue here. The example I used here was the image size. So like how large is the object captured?
Yeah.
Actually, that would result in how additional features can be analyzed. Yeah, so that can be one metric for the quality. Another thing is that so as we can see here, these like objects all appear in different viewing angles, and actually in many cases, so these objects can be partially occluded and so on. Take for an example, like here the example is vehicles, but when we're analyzing the activities of the person, so depending on which angle the camera is looking at, the target's activity recognition accuracy can vary very highly. So actually, we are trying to model these kind of like quality as a quantitative metric, and trying to devise an algorithm that can select these cameras adaptively so as to maximize the overall analysis quality and so on. Yeah.
Interesting. So it seems there's still a kind of a trade-off between efficiency and quality, especially want to figure out other like this kind of semantic information to decide the quality.
Yes, exactly. So basically, like we can process all the camera streams, and we can just use the best results, but that would obviously result in like significant resource overhead. So our goal is to like choose the best one so that we can minimize resource usage and as well as maximize quality and so on.
Thanks.
Thank you.
Okay, if we don't have other questions, so before we leave, just to mention, so please feel free to use the Slack to ask questions and answer questions. So if we don't have other questions, so I think this is the end for the first section. We can have a break for 10-20 minutes. So at the GTM, let me check, 11:30. So we will start our second technical session. So, okay, thanks for all your presentation, and see you soon. Okay, so I think this is the time to start our technical session 2. So in this session, we have 4 papers in this session, so which ranging from so kind of a PV fault detection to the light detection for embedded system, which range from a lot of interesting application. So our first paper, AI assistant cell level fault detection and localization in solar PV electrical luminescence images. So the presenter has a major in electrical engineering and mathematics from BITS Poland's Groha campus. He has worked on various computer vision problems as an intern at Microsoft Research India, and is currently working as a data scientist at the Deloitte. His research interests including language modeling, query understanding, and applied machine computer vision problem. So let's welcome Aham for his presentation.
Hi, are you able to see my slides? Yeah.
Yes, I can see you.
Hi. Hello everyone. Welcome to our talk on AI-assisted cell level fault detection and localization in solar panel electroluminescence imaging. This work was done at Microsoft Research India with my colleagues Akshay Nambi, Tanuja, Dhananjay, and Shiv Kumar. So over the past decade, with the increasing focus on climate change and sustainability, there is an ongoing investment in the deployment of solar energy, corresponding to nearly 580 gigawatts of installed capacity across 105 countries across the globe. PV solar modules, or solar panels as they are called interchangeably, are the building blocks of these solar installations. These PV modules can be classified into monocrystalline and polycrystalline modules. A PV module consists of a PV cell arranged in a matrix fashion, either in 12x6 or 12x5 fashion. Therefore, with the increasing capacity, it is important to monitor the performance and quality of these modules during manufacturing and operations by determining the fault type and localizing the fault for quick corrective action. To detect these faults, we mainly use EL imaging. EL imaging is also called electroluminescence imaging, which relies on the same principle as LEDs. In this setup, a solar panel is placed in a dark chamber, and then the current is passed into the solar cell that causes the light emission. This in turn is captured by an infrared sensitive camera and produces the EL image as seen here. So during the manufacturing or operations of solar panels, there are different kinds of faults that can occur in these PV cells, ranging from micro crack, branch crack, short circuit cell, PCVD marks, and grid defect. Micro crack and branch crack are cracks classified based on the extent of size or the spread of pattern of these cracks. PCVD marks are processing marks during manufacturing, reducing the efficiency of these solar cells. Grid defect are cases which are partial short circuiting between two busbar wires. And finally, short circuit cell is basically when the whole cell isn't working. The existing approach used for manufacturing quality assistance and fault detection for PV modules is solely based on manual inspection. It requires a human operator to inspect all cells on a panel visually within a short limited duration, like approximately 15 to 30 seconds per module. It is a laborious process and can introduce strain on the operators and leads to human errors in fault detection. It also increases the error rate depending on the expertise of the user and is subjective to change depending on the operators. This approach also requires an increased usage of manpower with minimal automation. So in our work, our main goal is to reduce the operator overload and eventually remove complete workload by using computer vision solutions to identify the faulty cells using our AI model. Now, the operator has to inspect only the faulty cells instead of all the cells to determine if there are faults in the panel. The impact of this solution is that it takes less time to analyze each panel with an increased efficiency, where more panels can be checked in lesser time. It also reduces human error by automating the process of fault detection and reduces the insurance and warranty liabilities on the manufacturer. Our solution mainly consists of solving three problems. First, we detect the panel level faults by classifying a panel as working or faulty. We detect cell level fault by localizing the faulty cells on the panel in a class agnostic manner like this. And finally, we classify the detected faults into their fault types as mentioned earlier in the presentation in a multi-class classification fashion. We do this by processing each panel image into a cell segmentation algorithm, which splits the panel into individual cells and then is fed into the CNN model for fault classification and detection. Cell segmentation algorithm. As part of a cell segmentation algorithm, we split the large PV module into 12 sub-images to parallelly process the sub-images on different cores. This reduces the time required to split the image into cell images. And the main challenges observed for cell segmentation are due to perspective issues in the image or due to incorrect stitching of an EL image. We address these challenges by performing the following operations, like masking, line detection, filtering, and extrapolation as explained thoroughly in our paper, to get more accurate segmented cells from our panel image with minimal errors. This is our entire pipeline for the fault detection. It is mainly bifurcated into two different networks. So once the bifurcation is done, we have two kinds of cells. Polycrystalline cells have much more noisier distribution of wafer marks on the cell, making it harder to detect these faults. Hence, we devise an efficient net B7 model to classify the cells into either working or different fault types. And if a cell is marked as faulty, it is further passed into our object detection model, RetinaNet, which localizes the cracks and grid defects present in these faulty cells and displays it in a matrix form as part of our post-processing pipeline. Monocrystalline cells, on the other hand, are passed into a faster RCNN model, considering the features of these cells are much more distinctive, and this two-stage detection model is able to perform well on the data. As part of our evaluation and understanding the robustness of our model, we use a public ELPV dataset curated by ZAE Bayan Group, which contains both monocrystalline and polycrystalline EL images, and then benchmark our model versus other models previously used in a similar context. The results of the detection model are as follows. For both monocrystalline cell image and a polycrystalline cell image. As we can see, we were able to achieve state-of-the-art on the ELPV dataset with our efficient net plus global average pooling model with 0.96 and 0.91 F1 scores for working and faulty types. We were also able to show the distinctive performance of RetinaNet and faster RCNN on both the monocrystalline and polycrystalline type images and also their inference times. Lastly, we show the class-wise performance of our efficient model with high recall scores, proving why we were able to trust the results of our classifier and use it as an input to the RetinaNet model. So in conclusion, we built a holistic system for detection and localization of faults in both mono and polycrystalline images for solar panels based on their EL images during production. It works with high accuracy at cell level and ensures that no fault is undetected by the system, indicating much lower false negatives. Lastly, the solution can be applied in both manufacturing and on-field scenarios for detecting faults, not only at panel level, but also at cell level, with the capacity to localize the fault within the image. Thank you.
Thanks again for the presentation. Do you have any question?
I've got a question. Thanks so much for the presentation. I'm curious in an embedded context, so we on-field context where a lot of solar panels would be inspected, let's say with drones flying over the solar panels collecting the image data. How resource efficient are the algorithms? So do you see that it would be possible to, or desirable to run them on, let's say, on processors on the drones directly, or is the processing too heavyweight and would need to be done in the cloud in the foreseeable future?
Thank you so much for this question. Most of our images are outsourced from either images captured via an EL setup or a drone setup. So there is a probability that there will be image stitching issues or perspective issues. So our solution currently is not deployed onto the drones directly, but these images are taken to a local area, and then using a cell segmentation algorithm, we will ensure that there is minimal error with respect to segmenting each of these cells. So it solves the perspective issue, which is very common in images captured via drones, because I think they're either shaky or not oriented exactly. So we fix that issue as part of our paper with a cell segmentation algorithm before processing it. But yes, it's not directly embedded into the drones as of now, but rather is processed, like basically the images from the drones are taken and then processed separately. And
is there significant variance in the image quality that comes from different drones, or do you think that your algorithm is quite generic and would be able to cover a broad set of drone operators, I guess, or drones flown by different operators?
That's an amazing question. We actually came across a lot of variation in the distribution of these images across different months and also across different drones and different manufacturers. To basically tackle that, we use a two-stage network for polycrystalline. So what we basically do is to ensure that there are no false positives or false negatives, which are occurring very frequently because of change in the distribution of data, right? Our efficient net model, which is a classification model, is much more robust to distribution, because while training, we ensure that the training data includes a variety of, it goes through a lot of data augmentation techniques as mentioned in our paper. So for example, we ensure that different brightness levels and also different augmentations of these data sets were included in our training. So because of that, it's much more robust to brightness, at the same time, the perspective of the input of the image. And because of our classification model, we are able to extract the faulty sets, and then using a RetinaNet model, right, we are able to detect where exactly in these cells are the faults occurring. So just in case we missed out on, like if we had some false positive, we'll be able to eliminate that as part of our object detection model.
Thank you. I've got another question if no one else wants to ask another one.
Yeah, sure. Please go ahead.
So just I'm curious in terms of the two separate processing pipelines that you have for polycrystalline and monocrystalline. It sounds like the efficient net is the more accurate of the two. So what's why exactly do you have a separate one for monocrystalline structures?
Yeah, you can also use the efficient net for monocrystalline purposes. But if you see our results, I'll just go to the results once. For a monocrystalline model, right, what happens is, even though the inference time is great on faster RCNN, we were able to see that a faster RCNN model has single-handedly, without going through any classification model, right, that is faster RCNN being a two-stage detector, it is able to directly localize the faults in a monocrystalline without going through classification first. Whereas in a polycrystalline context, what happens is, if you see here, right, there is a crack here and it's detected. This is a monocrystalline image. It's much more distinctive, and I can actually detect this much easier. But if you see a crack in a polycrystalline image, there's much more noise around the data. And as you know that as long as my my object detection module is not robustly able to detect it, we can't put it in production. So to ensure that there is no mistakes during production and also we don't incur costs on our manufacturer, we have to go through a two-stage system so that we can more accurately detect if a fault is present or not. First from a classification, which shows much more higher recall performance. So we can test it. And because of that reason, whatever faults are there, right, that would then be going through a RetinaNet model. And that's why we have a two-stage, two different model, a pipeline with two different models for polycrystalline and only a single model for monocrystalline because it's much more easier to detect.
Yeah. Thank you. And maybe one last question. In terms of on-field operations in different geographic locations in the world, what is your, so kind of, what do you think is the effect of distribution shift that you would get from, again, different sites where the models are used? So do you think that, how well do you think do you think a model would need to be adapted for every single site specifically, or do you think that it might be like within a country you could use the same kind of models?
Yeah, so I think for this thing, right, so an EL image looks approximately like this. And so even if you have a different dimension or even let's say different number of cells in a panel, right, that should be okay for a cell segmentation algorithm. But I think the question was if there is a change in distribution of data again across different areas of the country. So currently we've explored it in India, like different areas inside India. We haven't gone beyond our country to actually explore, but in general, the format of how these EL images look remain approximately like this. But just in case there is a change in distribution, our future plan is to basically include online learning where we can train at a frequent amount of intervals and ensure that the distribution change is not significant and the results don't drastically change.
Awesome. Thank you so much.
Thank you.
Okay, thanks for the insightful discussion. So if we don't have other questions, I think we can move to our next paper. So our next paper exploring co-dependency of IoT data quality and model robustness in precision cattle farming. So our presenter, Fans Past, is a third-year PhD student at the Institute of the Technical Informatics, Gates University of Technology, and the Complexity Science Hub, Vienna. So Fans received his master in cognitive science from the University of Vienna after completing his bachelor in software development and business management from the Gates University of Technology, and the second bachelor in philosophy from the University of Greece. So Fans is interested in pricing preserving deep learning models and the robustness to natural distribution shifts. So let's welcome Fans. So I'm assuming like Fans is presenting in the physically in the room, right? I'm not sure if it's on my problem, but I think I cannot hear you, hear your voice.
So now you should be able to hear me right. Okay, then again, hello and welcome to my talk about exploring code dependencies of IoT, data quality, and more robust imposition platform. And in this work together with financial networks. In recent years, IoT data and machine learning moving closer together. On the one hand side, we have IoT sensors which are getting smarter and smarter, and on the other hand side, we have models which do more sensor data, and they require even if such system consisting of sensors and machine learning models initially meshed, make it great over time due to sensor aging. Generally speaking, machine learning models are not really, it's not really easy for them to handle this kind of sensitive application because, again, also generally speaking, they are not that robust. So our contribution is to make data and more correctly code-dependent, testing state different cows. Lateness data from cows is a disease which is especially dairy cows where they are not able to walk properly. And this not only has negative implications in terms of animal welfare, but also negative implications in terms of economic implications for the farmer. Let's talk a little bit about sensors. We are kind of dividing into two different types of sensors. There are the one inside general purpose sensors, which are miniaturized sensors, which can measure different metrics, temperature, humidity, and they are optimized for a certain use case, usually in a certain range, but they're not limited to that use case. They work for any application in this range. Just think of a simple fever thermometer. The fever thermometer is defined working in the range around where there are around human body temperature, but you can use it for anything. So you cannot only measure body temperature, but you can also measure air temperature or water temperature. It's easy to finish. But most of the next step to that are application-specific sensors. These are sensors which are specific for a certain kind of application. In our context of precision livestock farming, there are cow activities, a cow activity index. This is it's an index, it's a kind of metric which indicates how active the cow was, how much it moves around the sensor. And those application-specific sensors, they consist of two components. The one inside the general purpose sensor, as I described before, which is measuring some metric, and also smart processing algorithm. The application-specific sensors use the measurement of the general purpose sensor, run some algorithms on them, and then display new metric or display new value. This is very useful for customers because the farmer is not really interested in the sensor readings of the accelerometer, for example. He is only interested in whether the cow is active or not. It has the sensors that are quite proprietary, and usually they are the intellectual property of the sensor company, and therefore they are the legacy trying to be easy to replace the sensor with a sensor from a different company. Let's talk a little bit about data quality. Many data, but the different kind of data is susceptible to natural distribution shifts. Natural distribution shifts are shifts depending on where and how the data is centered. The distribution of the data might vary slightly. For example, again, if there is an arm and you have three temperature sensors inside the arm, then you will get three distributions which are quite similar and still differ slightly. And this distribution shifts, they can also happen over time, and such a shift is very difficult to identify. This is why in this work we are focusing on artificial distribution shifts, which can basically be used to simulate systemic error and random errors in data. Yeah, failures connected data quality, there are outliers. Outliers are just data events which are quite significantly different from other for the other data transmission distribution. The thing about outliers is that outliers analysis they're just different, and it could indicate that this sensor failure could indicate this special event happened, or it's so if you face those outliers, you have to take a close look what causes them. About the model robustness, model robustness try to ask the question: is someone able to tolerate discrepancies between real and training data? In our work, we are going to use the isolation test to investigate this, and if the model is not very robust, then you have the possibility to do some kind of prevention. For example, you can denoise the data, smooth it, or therefore you can update or retrain. It's quite advisable if you do this in the field. You constantly check if your model is still performed well enough when you have a production system. I was briefly talking about isolation first, and isolation first very good method of detecting outliers in data. They are unsupervised, non-based, and they work similar to the end-to-end forest. They can have very similar idea that you construct a forest out of isolation trees. The isolation trees, you split the data randomly on features, and then once you have first trees, you traverse the forest, and outliers should have shorter paths before they are isolated. So the goal here is not that you are going to you're going to do some classifications in question, but in order to go to find the quickest path to relief, if it's a short path through the forest, then you are most likely to need outlier. As you can see here on this picture, where for this one outlier, it takes much less. It's quite quick. Now to the experimental part of our work, we are trying to answer the following three questions: how the different data contributions affect the accuracy of the models, how the different data contributions affect the isolation first score, and how does outpost correction deal with outliers and the distribution shift change the accuracy of the system. As I said, we get a data set from the domain expert with sensor data and predictions whether it becomes data or not. In order to see how robust the models are, we are educating those data sets and this slightly shift in the distribution to this data, and then we check how well the models perform on this budget. And we evaluate the accuracy of three different models: the expert model, the random forest, and XGBoost. The expert model was done by Katrina, our domain expert, with a very familiar flash sense, and the other models are just simpler simple machine learning models. But we treat all of those three models black box, so we just change slightly our data input and see how this affects the output. Our experiments were done on a training of the data set consisting of 5 data points, which we always split into 30% training data points, so 70% training data, 30% test data. And for the evaluation, we use 2 features: covers body temperature and the information covers. Those are the results. Well, as you can see on the heat maps, the lighter it is, the better is the accuracy, and the darker it was. We do this for temperature and activity index. In both cases, on the y-axis, we have the relative shift of variance, meaning we start from 0 up to 100% for the increased variance. And on the x-axis, we have the mean relative shift, where we increase the mean value for this distribution. And as you can see, especially the expert is very sensitive towards towards depreciation of the performance, even when we change the mean value for the mean value for the body temperature by 5%, we already see a significant drop. If we change it by 10%, different drops down. This is also true for reinforced texture boost, although the markets are much lesser degree. And the reason for that is because cow's body temperature is generally speaking always around 39 degrees Celsius. And if the body temperature changes, especially if the body temperature increases just by a few percent, this is an indicator that there's something wrong with the temperature. And therefore, the model is not really used to this kind of data. Therefore, the performance drops. For the activity index, as you can see, the data is much more developed that if you change the mean value, it doesn't affect the performance that much. It has remain effect on it. And the second question that you have is how the isolation request changes when we add distribution shifts to the data. And as you can see here, for the temperature, the isolation request score drops, which indicates that there are more outlets in this data set. And again, just by shifting the mean value for temperature by 5%, and the isolation request score drops quite significantly, meaning that the original trend isolation was considered a lot of outlets in this data set. For the next, it's quite fast how much changes. If we turn up the variance quite high, then you can see that drop, but it's a minor drop relative to temperature shift there. And now what we're doing is, when in case we, based on the values we get here, if the isolation request score drops below 100, we decided to retrain this the model on the new retrofit data set. And you can see what happens here every time. We have again diagrams for the expert model, first boost, and the models in red are those where we had to retrain. As you can see, we are showing here the difference between the originally trained and the retrained model for this new data. See much data, and as you can see, the performance, especially for the expert model, increases by up to 62% for temperature. And this was kind of to be expected, since if we do not have any kind of intervention measurement, the performance increases significantly. Again, for the activity index, there are some slight changes happening there. It's not slight improvement, but it's more or less the same. So current and future research directions is that robustness is currently a very big topic in machine learning research. It's especially interesting for images because if you have autonomous vehicles, you really need to have they need to be able to robustly process image data because there are many different real-life traffic learning situations that can happen. And the second reason is that machine learning could be challenging. Speaking, it's very interesting computer vision task, but even though it's a big topic at the moment, it's still quite an early stage. On robustness of IoT is on the other hand, error elimination something is still up and coming, because so far when people are talking about robustness in IoT context, it was more about device robustness, but the robustness was still on top of it. And the depiction of natural shift, as I mentioned, is quite difficult. I think it's also a very interesting research question, something that I can work on. So the conclusion of our presentation was that we investigate the relationship between data and quality. We propose to make them co-dependent by determining so we were able to improve the performance by up to 60%. Thank you for your attention. If you have any further questions, feel free to ask now.
Okay, thanks for presentation. So before we move to Q&A, so I just want to check a few. The sound is very hazy from my side, just to check it's not my own problem. So if it's a common issues, could we like to change the source to the one we used before? That one seems to be much better. So it's more soundable. So okay, so I think at the same time we can move to the Q&A session. So do you have any question? So I think I have a question for Franz. So although I didn't catch all the presentation in a very clear manner, but I found that what I have designed is tailored to a specific sensor or specific sensor type. Just curious whether the technique you propose has ability to transfer to other general sensor time series sensor data or other type of commonly used sensor data as well.
Should be correctly possible transfers to other types of sensors. It should be quite easy possible to transfer these other types of sensors, because the method that we propose is a simple one, but still very effective and straightforward.
Okay, so I think we can talk offline. So I cannot catch up what you say clearly, but we can chat on the Slack later. So anyone in the room has question for the speaker? Okay. So if not, let's thank the speaker, several speaker again. So let's move to the next paper, argument ontology matching through weakly supervised labeled augmentation. Our speaker, Fabio Malasca, is a Master of Science student at the University of Nepal, Federal Second. He has collaborated with some researchers for his master thesis, and he has done internship in the lab of NEC Lab Laboratory Europe, and his research interest is mainly focused on weakly supervised technique, in particular data programming. Let's welcome Fabio.
Yes, thank you for this introduction. First of all, let's a couple of things. Can you hear me? Okay, and then I'm trying to share my screen. Can you tell me if how can I? I'm sorry, just 1 second. Can you see it? Okay, then if everything is okay, I'll be presenting a work titled Ontology Matching Through Weakly Supervised Label Augmentation, because we studied an enrichment for data programming that actually belongs to the weakly supervised techniques family. And this enrichment is to solve a problem of ontology matching and consists in creating new labels in a certain way we'll see in this presentation, and for this label augmentation. Now, let's take a moment to understand what is ontology matching, what problems try to solve. Then we will move on the description of data programming in all these steps. We will see the classical data programming pipeline, Then the enrichment we tried to adapt to the ontology matching problem, and then we will compare some results. So what is ontology matching? Ontology matching is the process that states if there is a match or if there is not a match between two concepts taken eventually from two different ontologies. It tries to solve a problem of Internet of Things. In particular, there are so many devices, so many different devices that refers to the same object in different ways. So there is this problem of heterogeneity, and ontology matching try to fix it, try to give a solution to this. And two of its objectives are to associate concepts from different ontologies and to create a common knowledge base. As we were saying, ontology matching could output two different things. It is a match or it is a non-match. So basically we can see it as a binary classification problem where we have two types of labels. One, and this positive label corresponds to the match in this case, and 0 to the non-match. Now, since we are trying to solve a binary classification problem, there are a lot of solutions like supervised approaches, weakly supervised ones, and so on. And we have chosen one approach that belongs to the family of weakly supervised approach, data programming. Data programming works in many steps. This is a pipeline. First steps is to apply a set of heuristics to the whole dataset, obtaining noisy labels. Noisy labels because they are called like this with these adjectives, noisy, because they have to be considered not so accurate as it would be a ground truth, a label made by a domain expert manually. And in fact, this first step consists in the domain expert have to check the whole data set, have to see the features of these data points, and have to think and write some heuristics called labeling functions. Now, the point is to write a small set of heuristics, like 10, for example, instead of labeling data point by data point the whole data set. So we are creating like 10 labeling functions that will output 1,000 of noisy labels in the optimal case if we have 1,000 of data points, instead of labeling 1,000 of data points one by one. Okay, so the output of this first step is the creation of a labeling matrix where we have a number of columns equal to the number of labeling functions, in this example 10, and we have a number of rows equals to the number of data points, in this example 1,000. So we have 10,000 of elements in this matrix. That could be the noisy label given by a specific labeling function. In particular, to understand better, the first row is made of all the noisy label given to that data point, that is the first data point, by all the labeling functions. So first element is the output of first labeling function for the specific first data point. Second element is the output of another labeling function for the first element as well. And so we are producing this labeling matrix that has multiple noisy labels for each data point. Then we will pass this labeling matrix to a generative model. And in this second step, we will produce a set of probabilistic labels. So this generative model is basically a labels aggregator that for each data point takes these 10 noisy labels, for instance, and produce one probabilistic labels, a labels aggregator. But to understand better, one example, the most simple example of labels aggregators could be a majority voter. So for instance, it simply counts how many positive noisy labels there are on that row, how many negative labels there are as well. And basing on that proportion, it will output a probabilistic labels. So we are passing from a matrix to a vertical vector here, as is shown in this pipeline. Then we have to give this set of probabilistic labels to an end classifier in order to better classify the whole dataset. This end classifier could be a supervised classifier, like we used a random forest classifier with certain hyperparameters, and we will see later. However, the problem of this type of pipeline is the one cited below here in this slide, and we will try to fix it with an enrichment presented in the next slide. However, the problem is that we have to give to this generative model a labeling matrix that is dense enough, because otherwise this generative model will output bad probabilistic labels. Dense enough in what sense? So, for instance, we have said in the sense of density calculated in sense of the number of noisy labels for that specific labeling matrix out of the number of the total elements of the matrix, so this proportion. So for instance, if our 10 labeling function produced 1,000 of noisy labels out the total number of elements that are 10,000, we have a proportion of 1 out of 10, no? So this is the density in this case. Giving such a poor density to the generative model could produce bad probabilistic labels, because a proportion like this could mean that in the first row, we have just only one noisy label, and all the other elements of the row are basically -1, are abstentions, because labeling function could give noisy labels, positive noisy labels 1, negative noisy labels 0, but in case it doesn't know how to label that data point, it will abstain. So a first solution to create a more dense labeling functions is to try to cover more portion of the dataset by writing new labeling functions. However, this process could result time expensive, because usually a very limited set of labeling functions, few labeling functions that are immediate and simple come to our minds in very little time. Like we can think and write 4 or 5 labeling functions in half of a day, but then we have to keep writing new labeling functions, and this process could take many days. Also because these few immediate labeling functions come to our mind, but now we have to think maybe many more labeling functions that are more complex in terms of line of code, in terms of the knowledge that the domain expert has to have to write them, like natural language processing in the case of ontology matching. No? So our second solution is to produce more noisy labels, and so we want to make this labeling matrix more dense, producing more noisy labels starting from something we already have. The outcomes we already have from the small set of labeling function we already have. So we don't have to produce anything new. We don't have to write new labeling functions. This is implemented with these 2 new little blocks, reinforcement labeling, and the other ones that is called similarity of similarities. This basically is the same pipeline we have seen, but with these 2 new little blocks. Reinforcement labeling block try to label data points that have not been labeled by a specific labeling function, and try to label it the same way other data points have been labeled by the same specific labeling function. I will describe it with more simple words, I'm sorry. For instance, first data point, on the first data point, we apply the first labeling function. the labeling function does not know how to label it, and it will abstain. So first data point is unlabeled, is abstained. The same labeling function at the same time can label other 10 data points, for example. If these 10 data points are enough similar to the one we didn't label, why not to label this first data point as we labeled other similar data point? This is the idea. And so we introduced the concept of similarity, because we want to label a data point only if other enough a number of data points that is higher enough, but is similar and labeled, is similar to the data point we have not labeled. So we have to explain this concept of similarity. To explain this concept, let's take two data points. For instance, the first data point is made of two concepts, is a pair of two concepts, A and B, taken from two ontologies. For instance, A from an ontology, B from eventually another ontology. We want to build a relation between these two concepts of the same data point. Then let's take another data point that is pretty the same. So we have two concepts, C and D, with another relation. These two data points are similar if their relation is similar. We define the similarity like this. In particular, you can define a set of metrics, the number you want. We have chosen 3 metrics to define a relation between these two concepts. And in particular, they are Levenstein distance, spacey distance, text use distance. Levenstein distance expresses how similar two strings are, and how similar in terms of how many changes you have to apply to the first string to obtain the second string. The second metric, the spacey distance, uses some library function of natural language processing. The third one, text use distance, uses an encoder for text classification and semantic classification. Basically, these 3 metrics give a value that could, every value from different metric could be on a different scale. Like for instance, Levenstein distance has values in the scale that ranges from 0 to 100, for instance. Other ones, like spacey distance, have a different range, like 0 to 1. So all these metrics, all these values have to be normalized. And we used a classical min-max, minimum-maximum normalization. Then, in order to have a distance that stands for the similarity between two data points, we are aggregating all these values as this formula is showing here. Basically, you have to take the first value of the first metric for the first data point, then the second value of the same metric from the second data point, and have a difference, and consider that difference in absolute values. Then you will add all these differences, and this aggregation is our distance. What I explained is well written in this pseudo algorithm here. And all these values, before aggregating them, we can also put them in the dataset as new features, as it's shown in this table here. Okay, then we applied both this data programming pipeline to a dataset and confronted the results. First of all, we have to say that the dataset have been built by another group of researchers. They are from NEC laboratories, and they created a framework called VersaMatch. They created a dataset starting from 7 ontologies, this one listed here. They wrote as well a set of 11 labeling functions. They wrote as well the ground truth to see how the results were comparing to the ground truth at the end in the testing phase. Then, what's about the metrics and the end models which are used in this process? The metrics they used and the metrics we used as well are F1 score, precision, and recall. And we used these three metrics to measure the improvements. There is also a fourth one, but it's not relevant. In particular, accuracy is not relevant because the dataset is highly unbalanced. There are too many non-matches over the matches. And so we have every time an accuracy that is too high, every time, always. In order to solve this problem of the unbalancedness of the dataset, this group of researchers applied a method called pre-filtering. They labeled directly 90% of the dataset as a non-match, so they could work on a smaller dataset, 10%, the remaining 10%. But at the same time, there could have also some matches labeled in a better way in this 90% of data points labeled. So they used both the classifiers with this filtering and this and without the pre-filtering. The classifier used as end model is a random forest classifier, and the hyper parameters are this: 100 of trees, maximum depth equals to 4, the number of jobs equals to 1, and the number of random states equals to 1. We repeated the same experiment by applying the data programming pipeline, the classical one, and then we applied also the revisited one, the new one. Here there are first two results. On the left, we have the comparison of classical pipeline and revisited pipeline applied to the dataset using the whole set of labeling functions. And we will refer to this scenario as worst scenario because it's the only one scenario we perform a little worse, but not too much worse. It performs similar. Anyway, in these cases, since we are applying both the pipeline, we can choose the best results between them. In this case, the classical one, but all the other scenarios presents better results by applying the new pipeline. So on the right, we have another scenario made by considering a subset of labeling function. We are considering only 9 labeling functions out of the 11 ones. And as well for the other scenarios, we tested a lot of scenarios, every time changing this subset of labeling function. For instance, one time we considered 5 labeling functions out of 11, another time 6, another time the same number 6, but with different labeling functions. So in this best scenario, we are referring to this scenario like best scenarios because it have the major improvement of 11 F1 points. Then there are a lot of other scenarios that perform similar and place their improvements in the middle between the worst and best scenario. So they perform all similar. So we have just chosen a couple of them, and we are showing the difference between these intermediate scenarios with the worst and the best one. Here, instead, there is a little description of the 11 labeling function we used. And so in conclusion, yes, our approach works in this way. We basically are applying both the pipeline, and there is just a worst scenario because we are using the whole set of labeling function that there is already a large number of labeling function. While in other scenarios, we are using less labeling function. And all these other scenarios are closer to the reality, to the real life scenarios, because as we were saying before, few and immediate labeling function come to our minds in little time, while we have to take many days to produce other labeling functions. So when we consider a small set of labeling function, this scenario is closer to the reality. However, also in worst case, we can use the other classical pipeline, and we are working currently on taking the best results automatically. And I think that's all. Thank you for your attention. If you have any question, I'll be here live, or I'll be also in the Slack channel if you want to write any question, and I will answer your question in a written way. Or as well, these are our contacts. First, it's me. Second and third, they are the other two authors of these papers, and they can reply as well to your question. Thank you for your attention.
Thanks for the presentation. So I think so since we don't have enough time left for this session, so let's move directly into the next paper. We can either still use the Slack channel or use the Zoom chatting to ask a question, and answer question offline, I guess.
Okay, thank you again for your attention, and I wish you a good day.
Yeah, okay, thanks. See you here again. So, okay, so we move towards to the last paper in this session. Paper titled Through Spring Visible Light Sensing Empowered by Embedded Deep Learning. Our presenter, Hao Liu, is a master student at the Embedded and Network System Group of UT Delft, Netherlands, and his research interests including embedded AI, visible light sensing, and he's supervised by Professor Qin Wang and Professor Jie Yang. Let's welcome Hao Liu for his presentation.
Yes. Hi, can you hear me? Yes. I will start my presentation. Hello, my name is Hao. Welcome to my presentation for the work through screen visible light sensing empowered by the embedded deep learning. Let me first introduce the motivation of this work. Okay. In the past year, the pandemic has changed our life and habits. Now we need to work or study at home as much as possible. Regarding life, many things have been changed in supermarkets. We need to wear the facial masks or dress up like Spider-Man to reduce the chance to be infected by the COVID-19. Similar methods are also used by people in the elevators to avoid directly touch the buttons in the elevator. Some solutions have been used, such as using the toothpicks and tissues. In this case, we were wondering if we could draw the digits in the air. And for example, if we deploy some very simple photodiodes and in the elevators and the ATMs on one side of elevators and the ATMs, or put them behind the screen, and then use our fingertip to write the digits in front of the photodiode array. Okay, there is another motivation. The real full screen smartphone is becoming more and more popular starting from this year. Now the smartphones manufacturers prefer to put all sensors behind the screen, such as the Xiaomi Mix 4, ZTE Accent 30. In view of this, we were wondering if we can use a transparent OLED screen and put the sensors behind behind this screen, like these smartphones. Then the movement of our finger will reflect the light emitted from the transparent OLED screen, and this reflected light can be detected by the photodiodes and can be decoded. So in this work, we propose the concept of through-screen visible light sensing with reflected screen light. The animation on the left shows our ideas. Please note that we do not use the camera because it will bring some privacy issues and consume a lot of power. And the objective of this system is to design and implement an embedded system to enable eye-rating digit recognition system with the simple photodiodes. The key features are we leverage the reflected OLED screen and the simple photodiodes to design and run embedded AI algorithms, and we realize the real-time digit recognition on the embedded devices. However, such a system is not easy to build. What are the potential challenges? The first challenge is that different people could have different writing styles. For example, the shape of the writing digits could be different. The size could also be different. The writing speed could also be different. And the second challenge is that how to design a proper deep learning model in order to make it run on resource-constrained devices. The deep learning model requires a huge amount of the storage and a strong computation power, but as for the embedded devices, it only has few storage and low computation power. Next, I will present how we design our system and how to solve these challenges. First, I will introduce the system architecture and the prototype. The system can mainly composed by 4 components: the moving fingertips, the transparent OLED screen, the photodiode array, and the sensing algorithm. To make our system more stable, we build a PCB, and we put the transparent OLED screen on the top of the PCB, and the PCB is connected to the embedded devices Raspberry Pi 4 to do the digit recognition, and the result will show on this small monitor. To tackle the first challenge, different people could have different writing styles. We want to use the deep learning models because the deep learning models can not only extract the spatial features, but also process the time series information. But there is a problem is that deep learning model requires a lot of data, but there is no existing reflected light data. So maybe some people could ask, why do not use the MINIS dataset? Because MINIS dataset is the most popular dataset for the digit recognition. But here, it is a 2-dimensional dataset. But what we need is a 3-dimensional dataset, which should include the time domain information. So there is a simple way is to ask as many people as possible in our university to collect the data, but due to the pandemic, it doesn't work. So finally, we choose to use existing blocked light dataset, also named light digit dataset, which is a 3-dimensional dataset, includes the time domain information, and in total there are 174 types of digits, and in total there are around 20,000 drawings. The data records the shadow changes caused by the movement of our fingertip reflecting, blocking the ambient light. That means the finger moves, it will block the light, it will block the ambient light, and the blocked ambient light can be captured by the photodiode array. And the data are shown in the right picture. When the light is blocked, the data value will be decreased. Moreover, we collect some reflected light data as our mean test data. Each digit is repeated for 24 times, and each drawing lasts for 5 seconds. And this data describes the enhancement of the light caused by the movement of our finger reflecting the light. That means when we move our finger, the light emitted from the screen will be reflected, and the reflected light can be captured by the photodiode array. And the data has been shown in the right bottom picture. The enhancement of the light will lead to the data value increase. The differences between these two types of data are shown at the below pictures. To make these two types of data consistent, we flip the data. And next, we bring the data into the deep learning model. We have tried many different models. Finally, we came up with a customized conv-RNN model. The data we collected is a time series data with multiple channels. First, we evenly divided the data into many chunks to reduce the burden of the later layers. And then each trunk is connected to the convolutional layer to help us to extract the spatial features. And then we use the polling layer to do the information aggregation. After that, we use the GRU layer to process the time series information, because the GRU layer can store the previous step information and put it into the current step calculation. The result of the GRU layer are fed into the fully connected layer, and through the softmax, we get the result. Next, I will show you how we solve the challenge 2, how to make a complex model run on resource-limited devices. We adopt the most popular method, knowledge distillation. The principle of the knowledge distillation is that we have two models, a complex model named teacher model, and a simple model named student model. We first train the teacher model and transfer its experience into the student model, and the student can perform better. For example, there is an example showing in the right figure. The teacher first learn how to identify things by herself. Like, for example, identify the banana. She learned the banana can be identified by the color and shape. Then she transferred this valuable knowledge into her student. Next, I will present how we evaluate our system. We test 3 different scenarios: code start scenario, within subjects, and between subjects. As for the code start, we use the blocked light dataset for the training, and use the reflected light dataset for the testing. this scenario could help us to prove the effectiveness of the blocked light dataset. As for the within subjects, we split the reflected light dataset by for 80% data for the training and 20% for the testing, and the training dataset is augmented by the blocked light dataset. As for the between subjects, which is a typical scenario, we split the reflected light dataset by the participants. We use 2 participants for the training and 1 for the testing. And similarly, the training dataset is also augmented by the blocked light dataset. As for the difficulty, the cold start is most difficult one because there is no reflected light data in the training dataset. And on the contrary, the within subjects is the easiest one. Next, let me introduce the performance of the customized RNN model. We use the accuracy as our metric, and as for the cold start scenario, it obtained the 61% accuracy, which proves the effectiveness of the blocked light dataset. As for the within subjects, it arrives 91% accuracy, and as for the between subjects, it can get the around 70% accuracy. The reason for the difference of this scenario is because if we put more reflected light data into the training, the accuracy will be higher. Next, I will show you the result of the knowledge distillation. Before the knowledge distillation, the model has 512 GRU hidden units. And then we gradually reduce the number of the hidden units to get the best best distillation performance. As for the cold start and the between subjects, the number of the hidden units can be reduced to the 128, and while keeping the accuracy unchanged, it accounts the 86% reduction of the parameters. As for the within subjects, the number of the hidden units can be reduced to the 64, while keeping less than 10% drop in accuracy and 94% reduction of parameters. In this work, we propose the concept of through-screen visible light sensing and design air rating digit recognition system with reflected light. And we also customized an embedded deep learning model and conducted experiments to evaluate the performance. For the
Oh, did you lost a how? Okay, I think we somehow lost house connection. But fortunately the presentation is almost towards the very end. So let us wait for maybe 30 seconds or 1 minute to check if how can connect back. It seems that how has totally disconnected. So okay, so we can left the Q&A section to Slack or sending to email to Hal directly. So I think that's the end for the second section. We have almost an hour and 10 minutes for the lunch break for the local time, and we will come back at 2 p.m. For the GMT time zone. So see you later at 2 p.m.
Hi, I'm so sorry that, okay.
Oh, cool. You finally
Yeah, I have no idea what happens.
no problem. So yeah, if anyone in the room have question, you can ask Hal. So we have a casual, non-formal Q&A session. Okay, so I have a question. I'm curious, like I think there's a queuing application. I just curious, like how does the ambient light has an impact on the performance? Like if the light condition change, does it work? Or in general, do you need to do data augmentation when you apply your kind of system in different light condition scenario? Because once you reflect the light, the light surrounding around may have a huge impact on the performance, or it is not a problem at all.
I'm so sorry because the network is not stable, so I cannot hear very clearly about your.
No worry. Let's chat offline.
Okay, sorry.
No worry. Okay. So we officially like end the session. So let's have the lunch break for and let's come back at 2 p.m.
Dos. Ya. Ahora sí. Dos. Tricky.
Okay, welcome back. So welcome back to the third technical session for our workshop. So I see we already have the presenter. So let me first introduce our presenter for the first paper in this session. So we have our first paper, deep contextualized compression of compressive offloading for images. So our presenter, Bo Chen, is a PhD student in computer science from University of Illinois, at Urbana-Champaign. So his research interest lies in image, video processing, edge computing, and Internet of Things. His work is trying to explore a learned compressed method for mobile offloading technique. So I'll give time to Bo, and you can start your presentation.
Hi, Shusha, can you hear me?
Yes.
Cool. Hello, everyone. This is Bo Chen from University of Illinois, and today I want to present our work, deep contextualized compressive offloading for images. So nowadays, cameras have given rise to numerous applications, vision-based IoT applications. For example, traffic monitoring, autonomous driving, and smart house. These applications are making our life more automated and convenient. However, there is a problem that is impacting the performance of these applications. That is, the computation resource is limited on IoT devices like FPGA, Raspberry Pi, or NVIDIA Jetson Nano. To deal with this problem, one solution is to offload computation to a powerful server. However, another problem arises, that is, the bandwidth on this device is also limited. We cannot simply offload the raw image up to a server. To deal with this problem, multiple solutions have been proposed. One of them is to apply conventional image compression techniques like JPEG or WebP to the images that will be offloaded to a server, and then decompress the image and do the processing. However, the problem is that these conventional image compression techniques are not optimized for the performance of the IoT application. They are more optimized for the visual appearance of those images. Then a different approach is learned image compression. So basically, it uses machine learning techniques to compress data at the IoT device, transmit the compressed data to the server, and then reconstruct data at the server for further processing. But this approach causes another problem. That is, this machine learning-based compression techniques, they need an extra amount of computation power to do the encoding and decoding. But the compression overhead is not negligible on IoT devices. So this limits their application on those edge IoT devices. To deal with the computation overhead on IoT devices, an asymmetric autoencoder has been proposed. So basically, this autoencoder is unlike the previous work that used a symmetric encoder and decoder. It uses actually an asymmetric design. It consists of a lightweight encoder and a relatively complex decoder. And this design allows the encoding to perform faster on IoT devices. And with a more complex design of the decoder on the server side, this autoencoder can still reconstruct the image with good precision. However, there are still problems with existing learned compression methods. That is, they encode features in different areas on the input with the same ratio. So let's first look at the picture here, the top right corner. This 2x2 map is converted by a CNN filter into a 1x1 map. If we assume that the channels of two maps are the same, the compression ratio of features is 4:1. And for the bottom left corner, the 4x4 map is converted to a 2x2 map. The compression ratio is still 4:1. However, this is counterintuitive. In real life, we will have images where different regions carry different amount of information. According to Shannon's source coding theorem, less information should be encoded with shorter coding lengths, which implies less number of features. So to solve this problem, we propose a spatial adaptive filter, as shown here. This filter is able to compress different regions adaptively. For example, a normal region where we compressed with a 4:1 ratio, as shown in the top right corner of the image, while a not so important region can be compressed more compactly with a 16:1 ratio, as shown in the left bottom corner. And the blue region here denotes where the pixels does not carry information. So the bottom left area is compressed with a 16:1 ratio. So here we present our approach, DCCOI, Deep Contextualized Compressive Offloading for images. So how does this framework work? Basically, DCCOI is comprised of spatial adaptive encoder and generative decoder. So we have an image on the IoT device. This image will first be processed by the spatial adaptive encoder into a compact presentation Z. The data Z is transmitted over the wireless network to the edge server. Then the generative decoder will reconstruct the image using neural networks and feed the reconstructed image to a vision-based application, for example, image recognition application or object detection application. We shall produce image recognition or object detection result based on the image, the reconstructed image. And finally, the result will be evaluated by some quantitative metrics like accuracy. And our goal of this paper is to maximize the accuracy and minimize the size of the data that needed to be transmitted. And in this whole framework, the spatial adaptive encoder is the key component that makes DCCOI able to extract features adaptively and make it different from prior learning compression approaches. So now let's talk about the spatial adaptive encoder. Basically, there are two main components in the spatial adaptive encoder. One of them is the context extractor. So the input image will first be processed by the context extractor to generate context maps, which basically detects the importance of different areas. The other component is the spatial adaptive feature extractor. This feature extractor will extract adaptively filtered features from the input image based on the context map that is derived by the context extractor. Then the adaptively filtered feature will be quantized, and together with the filtering masks, they will be losslessly encoded to generate the compressed data Z. Now let's look at the context extractor. So the context extractor is basically applying layers of convolution to the input image. Like shown here, the first is a convolution with a kernel of A and the stride of A, then a convolution of kernel of 2 and stride of 2. Then the output of each layer is treated as the context map, which divides the image into equal-sized blocks. So if we look at the context map M2, it actually divides the original image into blocks of A by A. And each value in a context map indicates the importance of a block. So this is basically how we generate the context map from the input image. And next, we will talk about how we use those maps. So this context maps will be fed into the spatial adaptive feature extractor. This spatial adaptive feature extractor will generate masks based on the context. It will first generate n+1 masks from n context maps. So n is the number of context maps. In this example, n equals 2. The reason for n+1 is because the maps are complementary to the union of others. So the total number of masks is n+1. And each mask is generated by applying Boolean operations and upsampling to the context map. And for the details, we refer readers to read our original paper. And each mask will indicate whether to keep or drop a feature at a certain location. And different masks we generated allow filtering at different granularities. Also, another thing is that the masks are designed in a way that allows the feature map to be reconstructed to its original size, original shape through upsampling. So after we got those masks, we perform convolution with different dropping patterns based on the dropping or filtering patterns based on those masks. So basically, we will perform convolution to the image as usual. Then the features computed will be extracted from the convolution output based on the corresponding mask. And the extracted information will be concatenated to construct the adaptively filtered feature. And so the filter here is kind of like a learnable dropout layer that it's trying to exploit the most useful connections in neural networks to encode the image. And the features, more features filtered out at the latest state. So for example, the features that has gone through filter 1, 2, and 3. This means more compact compression. To recover the feature map, we will simply apply the nearest neighbor interpolation method. And of course, the compactly compressed region will lead to inaccuracy. However, the network is trained to reconstruct image from this incomplete feature map. And so basically, this is basically how we build the encoder. For the decoder, due to the time limit, we refer readers to read our original paper. Now let's look at the evaluation part. So the vision application of interest is object detection. We adopt the YOLO V5 model and the COCO 2017 dataset. The metrics is the mean average precision at 0.5. For the hardware, we use 2 IoT devices and 2 edge servers as specified here. And here's the networks. We consider the Wi-Fi and IoT networks in the evaluation. For the baselines, we consider 4 baselines, including JPEG, the de facto standard for image compression, WebP, image format for smaller images on the website, and INTP, which is interpolation. It encodes by evenly downsampled image and decodes by bilinear interpolation method. And deep COD is a state-of-art offloading approach that compresses images by imbalanced encoder. And here is a result. This figure shows the mean average precision and the compression rate trade-off of our approach and the baselines. So we can notice that DCCOI and deep COD are much better than conventional codecs like JPEG, WebP, and INTP. They are located on the left top side. If we look at it closely, we can notice that DCCOI achieves a mean average precision of 0.502 and the compression rate of 0.0039. And compared with deep COD, it roughly reduces 20% of the size than deep COD. Now let's look at the end-to-end latency. We evaluate the end-to-end latency on Wi-Fi and LTE and various hardware architectures. If you look at the case in Wi-Fi, we can see that the latency of DCCOI is slightly higher than deep COD by about 20 milliseconds. But when using LTE, the latency is much lower. It's about 300 milliseconds. So this shows our approach can improve the accuracy and compression rate trade-off, with not significant compression overhead. So as a conclusion, we present DCCOI, a lightweight, context-aware, and bandwidth efficient uploading framework for images. Our evaluation shows that DCCOI significantly improves the accuracy rate trade-off with small compression overhead when compared to existing compression techniques. And this is the end of the presentation. Thank you for listening. I'm ready to take any questions.
Thanks both for the presentation. Any question? Okay, so I think that I have a short question for Bo. So just wondering, so I think you have considered about the kind of the spatial dynamics to improve the compressor offloading. So have you think about how to further improve the whole pipeline by considering the dynamics of the data itself? So basically, if you have limited computation and network and things are changing over time, so do you think your kind of the design can directly apply to kind of the ways that we can dynamically adjust the size while vary with changing quality to meet the end-to-end requirement of the system?
That's a good question. So there are 2 things that I'm thinking about. One is to, because currently we only apply this method to object detection. So we want to apply this to a wider range of applications to see how this method performs. And another thing we want to do is that we are thinking about applying this filtering method to the neural network model itself. So we see this might be a potential way to reduce the size of the model, so that probably we can use this method to reduce the model size on the edge. So yeah, these are the things that we are thinking about.
Thank you. Okay. If we don't have any other question, let's thank our speaker again. So then let's move to the second paper in the session, federated learning for Internet of Things. So it's wrote by Tuo Zhang. He has received a Bachelor of Science degree in Electrical Engineering from the University of California, Santa Barbara in 2020. Now he is currently working towards a PhD in University of Southern California. His research interest is in developing transposing machine learning algorithm and systems. So let's welcome Tuo and his paper.
Hello, everybody. Can you see my screen right now?
Yeah.
Perfect. Good afternoon or good morning, everybody. Today, I will present our work, Federated Learning for Internet of Things, a federated learning framework for on-device anomaly data detection. This is a joint work with Chaoyang He, a senior PhD in our lab. Okay. Billions of IoT devices will be deployed in the near future, taking advantage of faster internet speed and possibly of the order of a magnitude more endpoint brought by a 5G or 6G era. With the blooming of IoT devices, vast quantity of data that contain private information of users will be generated. The high communication and storage cost mixed with the privacy concerns will increasingly be challenging to the traditional ecosystem of the centralized over-the-cloud learning and processing for the IoT platforms. It triggers a question, how could we use the data without the data sharing? If we go to a specific task of the IoT, such as the data anomaly detection, you will find there are several questions existing in this area. Firstly, some edge device create too little data to create a powerful detection model. And secondly, the privacy for each device is a significant matter. For example, people may infer the capacity of the manufacturer from its electrical usage for the industrial IoT users. So how to efficiently let each device to cooperate and how to let each device communicate without the loss of the privacy. To solve these two challenges and let everybody cooperate very efficiently, in our program, we construct the federated learning platform for the IoT devices. Federated learning is a nascent framework for the machine learning. Its basic idea is that training locally and average globally. The raw data of each device will not leave its origin during any phase of the training, which largely enhances the security. In our FED IoT framework, our overall goal is developing a personalized, weakly supervised, secure, and privacy-preserving federated algorithm and system for the realistic 5G data. In today's work, we mainly focus on the anomaly detection in the telecommunication network. For example, one of the most common security threats for the IoT devices is the DDoS attack, the distributed denial of service attack. Simply speaking, DDoS attack is an attempt to make an online service unavailable by overwhelming it with traffic from multiple sources that hijacked it by the hacker. In this graph, we suppose that the hacker hijacked some IoT device as the botnet to initial attack. The traditional way to prevent the attack is doing some verification at the victim side, just like doing the verification code every time we log into some account. But how can we prevent the attack from the bottom, from its original side? with the federated learning is highly impossible. We present a detection model to filter the traffic before it goes out to public. Our suppose is that we use the federated learning to train a global model and put it on the filter. And as long as the traffic goes out to the public, it will be filtered by the router first. If it's benign, we let it out. If it's malicious, we will keep it down. So our current contribution is in this two parts. The first part is algorithm. We design a federated learning framework, FED-Tech, for the IoT cybersecurity. And the second part is that we build the federated learning IoT platform for the realistic IoT devices and provide a comprehensive performance analysis, which will be discussed later in our presentation. To begin with, let's go back on the federated detect first. We choose the autoencoder as the core model. Autoencoder is a kind of unsupervised learning technique which focused on the reconstructed data as the same as the input data. After the training, the latent layer will be trained as a compressed algorithm for the data, which will extract the most significant features of the input. We will use the trained latent layer as our algorithm for detection. On the high level speaking, we will calculate the MSE between the input and output data for the benign dataset and use it as a threshold to distinguish the benign anomaly. The graph showing here is the histogram of the MSE for the benign data. It's clear to see that most of the data concentrate on the left side of the histogram, and the cutoff is very clear. As a result, we choose the threshold between the benign and attack as the mean of the MSE plus 1 standard deviation. As long as the inputs and outputs MSE is greater than the threshold, we will label it as malicious. We evaluate our model based on the three criteria: accuracy, precision, and false positive rate, the very traditional confusion matrix. Even though it's very traditional, but still a very accurate way to evaluation. Before I continue to the model, let me introduce a little bit about our data selection. The data we choose is a UCI open dataset, the botnet attack. It's gathered from 9 commercial IoT devices that actually infected by the Mirai and Bashlight attack. For each device, it contains 1 benign traffic data and 1 malicious traffic dataset. And the malicious dataset can be divided into 10 attacks carried by 2 botnets, the Mirai and Bashlight. Actually, this is the most popular open dataset that designed for the real IoT devices in the anomaly detection field. But if you have any other better choice or any other open dataset, please let me know. This is the features of that dataset. You can see that all the features is related to the telecommunication for the network. As I said, for each malicious dataset, it contains 10 different types and carried by 2 botnets and 2 very popular way to launch a DDoS attack, the Bashlight and the Mirai. For our evaluation, based on the UCI open dataset, we synthesize our own global testnet to evaluate the performance under the global federated learning model. As shown in the table, the global testnet is composed by all of the 9 devices, and the attack benign ratio is all set to 1 for the comprehensive analysis. We don't want the testnet to be biased by some certain kind of the data. In our program, we make the federated learning-based autoencoder. Specifically, we'll let all the devices connect to the cloud server. Each device will first train locally and then upload its model to the server. The server will generate a new global model for the whole system and send it back to each device. After that, each device will calculate its MSE sequence based on its own validation set, as we shown in the last table, and then upload the MSE sequence back to the server. The server will use the whole MSE sequence to generate a global threshold for each device to detect the anomaly data. For the system building, instead of using the TensorFlow federated and the Flower, this kind of popular stuff, then please let me introduce FEDML, the open source research library and benchmark for federated learning designed by our lab. This is the systems architecture that attempts to meet the goal. In the lowest layer, we designed the FED-ML core. Inside of it, there are two components, the distributed communication component and the training engine component. For the distributed communication component, it aims to support the MPI, MQTT, and the other backends such as the RPC. The high-level API is built based on the FED-ML core and also can be reused in many platforms such as the IoT platform or the others. Let me explain some features for the details. As for the high-level API of the FED-ML, the simplicity is the key. Here I use some example for the FED average algorithm to illustrate the API. To run the FED average, the first thing you need to do is specific to know the device or the topology. Next, you just load the dataset that you need to use. Afterward, you can create a model that can run based on the dataset on the local. As for the algorithm, you don't need to care too much about the details. You just call everything into one line. That's it. Only the 4 lines you can run a federated average algorithm. It's really quite easy. If you build by your own, it will take several days, but if you use our federated learning library, just in the 4 lines. But this is not the end. With this simple API, we support diverse algorithms. Besides the Fed average, we also support some very recent algorithms like the FedNova or FedOPT. Trust me, if you build your own FedNova, it will take at least a week. It's really abstract, but with our library, you can call everything in just 1 line. This algorithm can either support cross-device training and cross-silo training. We also support robotics and secure aggregation in our library. And some algorithm is designed by our lab. In short, the FED-ML supports 3 components, the optimizer, the various dataset, and the models. Currently, our FED-ML ecosystem have the 4 components, the natural language process, computer vision, graph neural network, and the IoT. Today, our work is focused on the Internet of the Things platform. If you are interested in our FED-ML library, please join our community. We are now ranked the 3rd for the GitHub under the federated learning, but the first 2 are the industrial leaders. Go back to the FED-LT platform. We designed 3 centralized baselines to compare the result to see the performance of the federated learning. The baseline A is train each device with their own data and guide 9 different personalized model and evaluate on a global set. The second one is combine some devices from the baseline A and then train 1 model to evaluate on a global set. The reason why we set up the baseline B is that consider some cloud computing company, they may have some historical data and they just want to use them, but they don't get all the access for the data. The baseline C is just like combine all data and train a very big model and evaluate on a global set. Because we only fed the model with the benign data, as a result, the more benign data the model met, the better performance it should have. So the baseline A, because it met the lowest number of the data, its performance may be the lower bound. In the same sense, the baseline C should be the upper bound for the performance. The result is here is very clearly for the global threshold. As you can see, as our predicted, the baseline A get the worst and baseline C is the upper bound. For the federated learning, it beat the baseline A and beat the baseline B and achieved a little bit lower than the baseline C. That can be illustrated by during the machine learning optimization, the direction of the gradient descent is shift after the aggregation by averaging, leading to a suboptimal, which may not be very suitable for the local evaluation target. To make sure, let's now go to the system part to make sure that the FED-ML is a platform that all-in-one to support the IoT platform. We need the abstract communication layer. As you can see, for the FED IoT platform, we choose the MQTT, the very popular communication framework for the IoT devices. We implement this result in a real IoT device, the Raspberry Pi, the very popular device for the IoT community. to test our implementation. The hardware setup is shown as here. We use 9 different Raspberry Pi to simulate all 9 devices and use the GPU server as the communication server. As you can see, our result on a Raspberry Pi is perfectly matched the CPU simulated result. The tiny difference is because we didn't fix the randomization, the initial randomization. On the more detailed result for the system implementation, as you can see, the FEILT platform does not take so much memory. So it's a very economic and very practical platform for the real deployment on the IoT, real deployment for the federated learning on the IoT domain. And also you can see the communication ratio takes about 40% of the total computation time. That shows that the communication is still a bottleneck for the distributed system. In summary, in our program, we successfully designed a FL-based autoencoder online non-detection system, and also we built the first federated learning platform for the real IoT devices, and is successfully deployed. From the system analysis, we can see is economy and practical. We hope our platform could give more support to the future research on the federated learning plus the IoT. We already make everything open sources and everybody could download it on the GitHub. Thank you very much.
Thanks for presentation. Any question? Okay, I have a question for I have a quick question. So actually, I'm curious for your like federated ML library, what's the workload? So I know that you mentioned that all the things can be very simple. One line of code of Python. It's more like a PyTorch style to build up the federated learning model by itself. But I just wondering the workload to really deploy the things instead of doing simulation. So is it the current library have a very kind of mature pipeline to support the engineer to deploy the model from a simulation-based algorithm to the real implement on different hardware backend? So is it kind of currently fully supported, or it is a wish can be like done in the future?
Currently, our library support instead of the simulation. Currently, our federated learning library support the NanoJSON and Raspberry Pi, and also the Android deployment for the real deployment. But the Android didn't have the on-device training. We are still working on this side, and yeah. But for the real deployment, we are still working on it, and it will be shortly released. Currently, it's the 1.0 version. I think the 2.0 version will be released in the next February or next March.
Yeah, sounds great. Yeah, I think the real deployment is way more complicated than the simulation. So I just curious, like your plan, but sounds a very promising and interesting.
Yes, thank you very much.
Thank you. Okay, so if we don't have other questions, let's thank our speaker again. So let's move to the third paper in the session, device or user rethinking. Okay, we have another federated learning paper, rethinking federated learning in personal scale and multi-device. So our presenter is Hansen Cho. She is a first-year PhD student in the School of Computer Science at Carnegie Mellon University. Before she comes to CMU, she studied in computer science at KAIST in South Korea. Her research interest lies in context-aware computing and mixed reality. And this work was done while she was at an intern at Nokia Bell Lab. Let's welcome our speaker.
Oh, thank you for the introduction. I'll start my talk. Yeah. So hi everyone, I'm Hyun-Sung Cho from CMU, and today I'll introduce our workshop paper, Device or User, Rethinking Federated Learning in Personal Scaled Multi-Device Environment. So this was part of the work I did over the summer at Nokia Bell Labs, Cambridge, with Akhil Mathur and Fahim Prasad. So for more than a decade, smartphones have been the personal computing data generating device. But with the advance of mobile and edge computing, users now own more than one data generating devices beyond the smartphone. For example, a smartwatch, iPad, earbuds, head-mounted displays for AR/VR, smart speakers, and more, which are all equipped with various types of sensors. So these multiple devices belonging to a user form a local sensor networks and offer intelligent and personalized devices. For example, wearable devices can track a user's physical activity and health, and IoT devices in smart home networks can recognize a user's speech command and automate home control. These multiple local networks together form a larger global network of devices. So the vast amount of locally collected contextual information are processed and used for intelligent and personalized services with the help of machine learning algorithms. So nowadays, by machine learning, we usually refer to deep learning, which consists of two key processes, training and inference. And in the training process, models are trained using large sets of labeled data and neural network. And in the inference process, the trained models are used at runtime to process real information. So when we train deep learning models in distributed sensor networks, the most common approach of distributed training is centralized learning, in which mobile and edge devices send their raw data to the cloud server, and the server trains a deep learning model with the large data set collected from all these devices. However, this threatens privacy by exposing private data to the server, and the communication cost of raw data is very expensive. For example, if we imagine sending raw 4K video streams from a camera network to a centralized server, indeed it could be very expensive. So yeah, and also having one central model is prone to resulting in inconsistent accuracy across devices. So to cater for all these problems in centralized deep learning, the concept of federated learning has gained popularity. In federated learning, instead of sending raw data to the server, each device locally trains models on local data samples and only exchange the parameters to generate a global model. And this federation preserves privacy as data remains in local devices, and communicating model updates is a lot cheaper than just sending the raw data. So as models reside on the devices, we can also think of opportunity for achieving consistent accuracy through personalization as well. So in conventional federated learning, each of the remote data generating device is considered as an FL client, and each device interacts directly with the FL server to perform distributed training. And we call this traditional architecture as the device as client, or DAC architecture. However, if we really think about applying this FL architecture in the multi-device local sensor network settings that I described earlier, it brings up a new question. Instead of each device, can we treat each user as an FL client so that we can exploit the natural affinity between the devices of a user? So if you recall our examples of body area networks or smart home networks, there are natural associations that are shaped by sensory devices residing in the same local network, such as personal walking behaviors and gaits, or ambient acoustics or lightings that are unique to a local network. However, the current device as client topology treats each device as an individual client and ignores these natural associations. So this leads to inconsistent performance across devices within the same network. So applying a new user as client, or UAC architecture, is expected to have some benefits in terms of improving the statistical performance, the accuracy and convergence rate, and also the system performance. So first of all, having this user level abstraction facilitates ensuring temporal alignment between devices for better visual representations. And secondly, training the devices of the same user together can mitigate class imbalance in data across devices by other devices filling in the missing knowledge. And lastly, a user-level abstraction allows better management of system resources in mobile, wearable, and IoT devices, which are usually lacking these system resources. And yeah, with better awareness of each device's resource profile, we can achieve better management of these resources. So in this workshop paper, we present our findings from our early experiments about the benefits of UAC architecture over the DAC architecture. So in the first experiment, we investigated the performance comparison between a DAC architecture and a UAC architecture using the same data set, the real-world data set for human activity recognition. So this data set consists of 7 accelerometer and gyroscope device sets placed at 7 different body positions, and it contains data for 8 human physical activity classes. So for the device as client settings, we treated each device as a client, so having 105 clients in total. And for the user as client setting, it's the same data, but instead of having 105 clients, we aggregated the device data for each user and treated each user as a client, so resulting in 15 clients in total. And when tested using the deep learning models DeepConv LSTM and ResNet NLP, which were used in previous human activity recognition papers, the results show that there was performance gain with UAC for about 15%, and with using the DeepConv LSTM model, and about 18.9% of performance gain with ResNet NLP compared to the DAC model. And we explain the reasons for this performance gain as in twofold. So firstly, even though the total number of data samples used for vector learning are the same in both settings, UAC has more local samples on each client by virtue of its architecture design. So this could lead to faster and better convergence of the local loss on each client, and in turn leads to higher accuracy of the global model. And secondly, in the UAC architecture, the local data sets are statistically heterogeneous as they contain data from multiple devices, each with a different data distribution. So we expect that this local learning on these statistically heterogeneous device data sets is advantageous for learning more generalizable feature representations, which in turn improves the generalizability of the global model. So this experiment has some limitations and it leads to open questions. So first of all, considering the expensive cost of communicating raw data, it's not actually efficient to aggregate the raw data from all devices that belong to the same user. So this draws a question, then how can we apply collaborative training not only across the users, but also between these local devices of the user instead of sharing the raw data by aggregating the data set? And second of all, in this experiment, we assumed that we involve all 7 devices of a user in the training, but sampling all devices for each training round could be very expensive. So can we achieve a similar level of performance while reducing the training cost by sampling only a subset of devices? And on top of that, mobile, wearable, and IoT devices usually have limited resources and availability. So can we take into account this availability and resource status of devices in device selection? So in the second experiment, we tested 3 different device selection strategies for vector learning in multi-device settings. So the first is selecting the same device on each client in a given round. So this achieves a homogeneous setting of the training. And the second strategy is selecting just random K devices on each client or user. And the third strategy is selecting K random devices, but sampling them from P largest device data sets with a higher probability. So if the dominant devices will get more chance of being sampled in the round. And the results show that the random selection actually achieves higher test accuracy than the dominant random or homogeneous selection strategies. And the takeaway from this result is that it is really important to maintain the statistical heterogeneity between devices that are selected on each client in each round for generalization of the global model. And this further leads to more questions now. Are there better strategies than random sampling to better ensure statistical heterogeneity? And also, besides this accuracy performance, how do we incorporate this consideration of systems heterogeneity or the resource availability? So as our last experiment, we devised a simple data-aware and resource-aware device selection strategy called FMD, FADMD, that considers statistical and systems heterogeneities across devices in device selection for each training round. So as a data-aware strategy, FADMD prioritizes devices with higher local loss, higher loss on global model. And as a resource-aware strategy, FADMD prioritizes devices with higher system resources. So as a proof of concept, we devised a simple scheme that first picks a candidate set of devices for each user, which are above a battery level threshold T. And among these candidate devices, FMD selects K devices with highest local losses. And for the experiment, we used the same data set, the real-world HAR data set, and we emulated the battery drain based on energy profiling on NVIDIA Jetson devices with simulation. So devices participating in the training experienced 2% battery drain per training round, and the non-participating devices experience 0.5% battery drain per training round. So for the parameters, we set the number of devices per user K to 1, 2, and 3, and we set the battery level threshold to 60% for this experiment. And yeah, the results show that using the UAC architecture shows a slight improvement in the accuracy around 2% better than the DAC. And it's notable that the improvement in performance is slimmer here than the previous experiment we did when we aggregated the data set. So we think that is due to the smaller data set size and also less statistical heterogeneity among the devices in each client. And this is due to the device selection of K devices, which is less than the all 7 devices that we used in the previous experiment. So this, in a way, it aligns with our previous findings that it's important to achieve high statistical heterogeneity among the devices selected in each training round, and also maintaining a number of data set in the local device is in the local client is also important. And besides the accuracy, we also plotted a CDF plot for the remaining devices above battery drain limit due to FL. So the x-axis is the target amount of battery drain, and the y-axis shows the percentage of devices whose amount of battery drain is below each x. So we observed that applying FADMD in the UAC architecture results in more percentage of devices remaining above the battery drain limit than DAC. So for instance, after training FADMD in UAC, 5.9% more devices have below 20% battery drain than DAC. So this indicates that UAC has a lower system overhead than DAC while still achieving higher accuracy. So based on these early stage results, we discussed future directions for federated learning for multi-device local network settings. So we explored various device selection strategies. However, we did not perform any client selection in each round. So more specifically, client selection algorithms will need to consider that each client no longer has a single data set, but a number of non-IID data sets collected from different devices. So incorporating this into the client selection algorithm, not only the device selection strategy will be important. And also we focus on the performance of the global model in the UAC architecture, but prior works and recent works have shown that a global model does not always generalize well to clients with smaller data sets and whose data distribution varies a lot from the global distribution. So we hypothesized that the UAC architecture could benefit from personalization or local optimization method as well, not only just training the single global model. And as opposed to data sharing, we may need to design collaborative training techniques better, even among local devices, to learn useful features or a local model from their data. So one possible design is to support local collaborative training by running a two-step federated learning that consists of a global FL and local FL. So the traditional way of collaborative learning in global FL can be also transferred to the local setting as well. And one device of a user, possibly one with the most computing resources, can act as a dummy FL server within the local setting, and it can coordinate the local federated training among the devices to learn a local model separately. And these weights of the local model can be then sent for aggregation to the global server to train the global model. So this resembles the concept of vertical federated training, which was proposed before, but we think that it could be further applied to these local network settings with personal scale or multiple devices. Yep, so yeah, thank you for listening to my talk, and I'm happy to take any questions or discussions since this is a positioning paper that we presented. Yeah, thank you.
Thank you for the presentation. So any question?
Yes. Can you hear me?
I think we cannot hear you very clearly.
Okay. Now, can you hear me?
Yes.
Okay. Yeah, hello. My question would be, since you now have multiple devices per user, have you thought of potential privacy implications for the user? Because at least to me, as far as I understood, if you have multiple devices per user, it's also more likely that some privacy information gets leaked. Did you thought about those things when you were conducting your work?
Right. Yeah, so I agree with your point about that it could further impose the privacy concerns because we are considering collaborative training among these devices of the same user. And it would matter less if the devices of the same user belong to the same vendor, but in most cases it doesn't belong to the same vendors. So sharing the raw data itself among devices might not be very practical nor efficient. So that's part of the reason why we were why in the last discussion slide we were proposing a new way of local collaborative training, which can also involve federated learning at the local user level. Because then we don't need to share the raw data, but rather we can just share the parameters of the deep learning model, which is in a sense the core essence of the federated learning concept itself. Instead of sharing the raw data for privacy, we instead share the parameters of the model. So yeah, as a future direction, and we are currently working on further extension of the project, and we are considering a more privacy preserving and more efficient way of collaborative local training instead of imposing further privacy concerns.
Okay, thank you.
Thank you for the question.
Okay, thanks our speaker again. So let's move to the next paper. So our next paper is sensor virtualization for efficient sharing of mobile and wearable sensors. The speaker, Jian Xu, graduated from the PhD program at the Stony Brook University and currently works at Oracle Cloud Infrastructure in Seattle. His research is mainly focused on improving the usability, programmability, efficiency of the mobile and wearable system. So let's welcome Jian for his presentation.
Yeah, thank you, Shosao, for the introduction. So, hello, everyone. I'm Jian from Stony Brook University. Currently, I work at Oracle Cloud Infrastructure. Today, I'm introducing the paper, Sensor Virtualization for Efficient Sharing of Mobile and Wearable Sensors. As we all know, mobile and wearable devices are heavily used in our daily life. They are becoming a part of our bodies that make our life better and more convenient. For instance, people can use wearable devices to monitor their workout process or health status, getting feedback from the training, picking up phone calls using the smartwatches without holding the bucket phones. So we conduct a pilot study on the top 250 Android smartwatch apps, and there's some interesting findings. We've seen that only 9% of those top 250 smartwatch apps are sensor apps. And that support use cases such as tracking activity, workout apps, or navigation, mobile payment apps. Those are very limited number of use cases for wearable devices. And also, according to an existing study, a common complaint from wearable users is that there's a lack of functionality for wearable apps. So here's one possible reason that the problem we found is that there shows a high barrier for developers to leverage sensors. Developers needs a lot of effort to get a sensor working, such as like it needs process the sensor data, like do normalization, denoise, processing those sensor signals, or take care of the data communication across devices. And it also requires customized data to work with heterogeneous devices. So the motivation of this paper is to enhance smartphone apps by leveraging wearable sensors. So we try to eliminate the barrier so that developer can utilize sensors in more convenient way. We envision several benefits of leveraging wearable sensors for smartphone apps. The first one could be overcoming hardware limits. For example, some old brand smartphone, they probably not equipped with some more advanced sensors, such as like NFC sensor, so that those phones are not able to use Samsung Pay, Apple Pay, something like that. So to solve this, we can just enable the smartphone to use more advanced wearable devices, such as like some smartwatch and NFC sensor, which scales up more compatible apps for all smartphone devices. The second case is that it improved quality of experience. For example, users do not need to hold bucket phones. Instead, just by waving hand gesture to control video game, like as the feature, you can see that. So they can possibly provide better experience according to our study. Yeah. And another case is that it also can provide some new interaction modality. So such as like pausing YouTube the YouTube video by just hand waving gesture. You don't need necessary to tap in the screen. Instead, just define whatever gesture you would like to. So those nice use cases are our paper that trying to achieve. However, it is not easy to use wearable sensors for smartphone apps without considerable developer effort. As we mentioned previously, that it requires communication protocol, sensor data processing, it even needs to modify existing logic code of the app to fit in for the wearable sensor data. So therefore, we designed a system SenSysWare to achieve the goal to enable smartphone apps to use wearable sensors with minimal development effort, there are a couple of challenges that we need to address in order to achieve the goal. The first one is that it requires high development effort. As we showed previously, that developers have to take care of the sensor specification, network communication, signal processing, and so on and so forth. Another is that we need to take care of the heterogeneity of sensors across devices, because these sensors, they have different specification. For example, like a motion sensor, like accelerometer, it has different orientation, position, so that even the same kind of sensor, they yielding different values. So to address those challenges, we designed several layers of the system to take care of it. The first layer called sensor metaprogram. That is the layer that metaprogram is for developers to easily specify the sensor mapping rule, so that the remote sensor just could fit in the local device without much effort. That is the only part that needs the developer to be involved with. The next layer, the sensor mapping layer, actually implements the mapping logic. It combines sensor data with metaprogram. This is the layer handles the heterogeneity of the sensors. And the final layer, the underlying layer, virtual sensor service, is responsible for sensor replacement of local sensors, the wearable sensors, which also includes the communication across devices. So let's go deeper to have more insight about the system. So you can see currently this is a current situation of how smartwatch does for the sensor. Why the smartwatch sensor, the smartphone sensors, it dispatches the sensor event to the sensor service, which finally being dispatched to the smartphone apps. So for this one, the blue part shows sense wear parts, and metaprogram is the only step in both human in the loop, and the metaprogram specify which remote sensor to use, how to use the remote sensor locally, and sensor mapping rule, as the sensor mapping layer maps the remote sensors to local device by parsing the metaprogram. And those phone proxy take care of the communication. And so the virtual sensor service reads the information by the metaprogram and get it from the proxies, and finally dispatch those to the smartphone apps. The reason that we inject the sensor in the lower layer in the sensor service, because it will make the virtualization, the sensor virtualization, being more app agnostic, which is a more generic solution, so that if any future sensor API changing on the up layer, it won't affect sense wear functionality at all. So let me introduce something more about the metaprogram. And we designed metaprogram framework just to minimize the developer effort. And this is the only step required from the developer. It allows the developer to specify how the sensor gonna be mapped across heterogeneous devices, like and decide like what kind of sensor I'm gonna map with from and to, and the sensor frequency, and some more deep customization function for mapping. Here's one simple examples for the metaprogram. You can see that I just want to mapping the same kind of sensor, like accelerometer sensors, and by using different frequency. That's quite easy to write. And after parsing the metaprogram, the mapping layer actually implements the sensor mapping rule. There are two cases of mapping. The first case is that one-to-one mapping with the same kind of sensors. As you see from the figure on the left, that we're trying to replacing the same motion sensors by using the smartwatch sensors instead, so that you can just waving hand gestures to control the video gaming on a smartphone. The second case is that mapping with a different kind of sensor. As you see from the figure on the right, that we're trying to replacing the ambient light sensor and the proximity sensor on the smartphone by using the proximity, the ambient light sensor on the smartwatch. So here's an example that we just waving gesture on top of the smartwatch to control the smartphone. For example, like change the volume or lock the screen. And another point to clarify is that mapping the sensor mapping we refer to does not necessary to be a sensor fusion. Instead, we just replace the local sensor data by remote sensors. One quick background of why we still need to do one-to-one mapping even for the same kind of sensor. Here's an example that you can see that smartphone and smartwatch, they can have different orientation, right? So that the XYZ, they're yielding different values, even they're the same kind of sensor, like accelerometer or gyroscope. So here's how we tackle with one-to-one mapping with the same time. We actually consider mapping of those sensors as a case of affine transformation. And this is because affine transformation preserves distance between points. And performing such an affine transformation requires multiplying the value of affine transformation matrix, as you see from this equation. So the key point is that we just need to find out this affine transform matrix like A1 to A12, so that the XYZ, the value of variables, can be just multiplying this affine matrix to getting the new mapped data which fit in on the smartphone. So to compute this affine matrix, can be done by calibrating the sensor. The calibrating, we mean that in the beginning of the usage, we asked the user just to pause, just hold the smartwatch and the phone for 10 seconds after collecting those data, and we just use piecewise linear regression just to calculate out what is affine matrix. So after this transformation, to calibrate sensor data, it can be fit well on the heterogeneous devices. We'll provide more result on the evaluation. So another case is that one-to-one mapping the sensors with different kind. This actually requires a callback function to specify the mapping rule. As you see from this simple meta program, the last line shows the on-sensor override. This is the function name, that the callback function that let the developers to customize to define whatever behavior they want to do the mapping. So you can see that this is the function, the callback function, that up to the developer to decide. The input parameter is from the watch data, and it actually returns the beam mapped data that are going to be used by the smartphone. So therefore, we just leave the flexibility to developers so that they could decide that whatever behavior they would like to perform the mapping. And we implement SenseWare and on the Android ecosystem, and we generate 6 wearable sensor apps. We divide it into 3 categories. The first category is that we replacing the same sensor, like the accelerometer with the same, and as we mentioned previously. And the second case is that we replacing different kind of sensor, which also like replacing the proximity sensor with the ambient light sensor, as we also mentioned previously. The third case is that we replacing the local haptic vibrator with wearable vibrator sensor. That means that if we got vibration like on the smartphone, actually gonna be vibrate on your smartwatch. That will give you more haptic on your wearables rather than from smartphone. So here's the lines of code that it took for getting or generating those sensor apps, get it working. So we can see that it just takes within 20 lines of code. We measure the duration it takes from the sensor generated on the smartwatch to the sensor received on the smartphone. The red dashed line indicates the threshold of the 220 milliseconds, which is the threshold of human perceivable response time. And according to the existing psychophysics study, that user could perceive delays obviously for delay that are above the threshold. So therefore, that SenseWare can achieve acceptable latency, as we see clear. And we also measure the 3 distinct gesture mapping, so to see how the performance of the mapping algorithm works. So for example, like the gesture A, that we rotate the smartwatch anti-clockwise and move the smartphone left, and the gesture B is that we're raising the smartwatch and move the smartphone forward. something like that. So we're trying to test different scenario of those mappings and see how good they are performing. And measure the root mean square error for each case respectively. As we see that the precision for each case, they were higher than 90%. Yeah, so therefore our sensor mapping approach has high precision mapping performance, which is practical enough for use. So here's some future work that we plan to do. We plan to improve power consumption because that actually why we replacing the wearable sensors, replacing the local sensor by wearable sensors. And the local sensor is not necessary to be turning on. So we plan to reduce that one. That will drastically save power. And we also plan to conduct more user studies so that we have a better evaluation and feedbacks from the sensor about the sensor. And we also plan more machine learning approaches to improve the sensor mapping, such as CNN. We also plan to support more hardware and sensors, such as support NFC, heartbeat rate sensors. So the conclusion is that we design senseware that decouples sensor stack from app logic to leverage wearable sensors. And senseware provides a meta-program framework that drastically lowers the entry barrier for developers to use the wearable sensors. And senseware achieves acceptable sensor latency. Thank you for your time watching.
Thank you for your presentation. Any question? Okay, I think I have a question for Jen. So actually, I enjoyed the idea and how you motivated example. I think it's very interesting to say how to virtualize the sensor to reduce the efforts for development. So I just I think well, take example. I think in your presentation mentions there's a way to do one-to-one sensor mapping. So what I understand is that, so for example, instead of using a accelerometer on my phone to do the gate detection or localization or tracking, I would like to use my smartphone acceleration to do that. And all the kind of mapping is done automatically by your kind of library if we can do some calibration at the beginning. But I feel that so this task is way more complicated than what you mentioned in the slides, because for example, so let me put the question in a kind of simple. So did you consider the relative motion of these two sensors after the calibration step? Because at beginning they can be defined by a static affine transformation matrix, but as a time, in follow-up time, so these two sensors are kind of moving in different orientation direction. So then if you just do a kind of the simple static replacement, it doesn't. Yeah, it can solve some problem, but I don't think this is an ideal sensor virtualization for me. So
okay, I see. So your question is that whether this, for example, we mapping the same kind of sensor, does it really helpful, or does it really so much use does it really provide better user experience? Is that your question?
Yeah, somehow. Does that mapping is automatically can do the real mapping, real physical quantity to do the one-to-one mapping, or is that I do the mapping at the beginning, if say somehow deviate from the calibration process I do before, then it doesn't work that much. So is it type 1 or type 2? I
okay.
Just curious.
I see. So you mean that after calibration, then
Yeah.
probably might drifting somehow, and then probably you will stop working after duration of time, right?
Yeah.
Yeah. So that's a good question. For example, some drifting happening because sensors always have a lot of drifting issue that on smartphone and smartwatch, and then they probably start deviating, and then you just stop working, right? So I would say that there's a tons of a lot of research on how to like to eliminating or addressing those drifting issue. But like, so drifting is a very big topic. But according to our study, we did some pilot study on the one-to-one mapping. So there's some user study that it shows that since we scoping the user study, say around like 20 million under 20 minutes, and then to see how the user feel about this mapping, and they have positive feedback. They're showing that, hey, this is a really nice interaction model, so that we can just free it up from our hands, so that we don't need to holding that, and then we can play with that, and then that works well according to feedback. However, we haven't considered much about the drifting after, say, a few hours. That's out of that probably also is a good point for us to consider in the future, because the drifting is really an issue according to the existing study. A lot of like drifting paper on that. We were considered to trying to apply those technique to addressing those, or at least to minimize that effort. Those effect. Yeah, that's a good point actually.
Okay. Yeah. Thank you. Thank you. Okay. If we don't have other questions, let's thank our speaker again. So then let's see. So then we are moving towards the very end of the paper for this whole workshop. So our final paper, decentralized federal learning. So we have third federal learning paper actually in this session. Decentralized federal learning framework for neighborhood, a case study on residential building load forecasting. So our presenter, Jiechao Gao, is a PhD student in computer science department at University of Virginia, working with Professor Brantford Campbell on IoT data privacy and energy management. Okay, let's welcome our speaker.
Can you see my screen?
Yes.
Okay. Hello, everyone. My name is Jiechao Gao. I'm a PhD student in University of Virginia. So today my topic is a decentralized federal learning framework for the neighborhood, a case study on residential building load forecasting. So the IoT trend moving towards more in intelligence way. So right now we have like smart home applications. We have like smart wearables. We also have like smart city applications such as the smart energy grid, smart transportation system, and also smart industrial like manufacturing robots. So all this kind of AI plus IoT applications have provided users with opportunity to improve their user experience. Most of these smart applications often require a large number of diverse training data to accomplish a robust model. And thanks to the number of IoT devices are increasing dramatically, we are soon entering the world of Internet of Trillion Things, and thanks to the growing number of IoT devices, it makes it possible to collaboratively train the model. So all seems pretty fine. So what is the challenge? So one of the challenge definitely should be the data privacy problem. As we can see in this figure, so all the kind of internet users are having some privacy concerns growing through time. Basically, like over 50% of the users, they have concerns about like sharing their data through the internet. And it is not only in the US, it's like a global thing. So existing approaches for collaborative training can be categorized into two ways. The first one is the cloud-based system. So basically, all the users, they have their local data collected, and they transfer the data into a cloud server, and the cloud aggregator gonna combine all the data for the training purposes, and it will be a global model sending back to the localized users to perform applications like load forecasting, predictions, objective detections, things like that. And recently, another approach is fairy learning. So I think, in our section, I think, 3 of us have already said that, like the fairy learning based model. So I'm just gonna be a little bit brief on this one. So basically, all the users they have their data kept locally, and they have a say machine learning or deep learning model, and they're gonna localize train that and send out the gradients, the parameters, the model into a cloud server, and the cloud will aggregate that through algorithms like very average, or there are a lot of kind of different like averaging techniques developed, and the cloud central server gonna send back the model, and all the users gonna do the localized training, the localized prediction. So for fairy learning model, I think one of the goal is the people can collaborate train the model, and also they're gonna less be worried about the privacy issue. And one more thing is that for fairy learning framework, it will be more easier to do like personalization stuff, or apply different technologies to enhance the privacy further. For example, like differential privacy methods. And the above approaches are aiming for collaborative training. So so these existing approaches solve the privacy challenges, like from our point of view, not so much. So all the cloud-based methods and fairy learning-based methods, they're gonna need to aggregate data or intermediate model training updates in the cloud, which may cause direct data leakage, or training examples gonna be reconstructed by a model inversion. So there's still gonna be a chance that your privacy is now preserved in this kind of architecture. And according to a research that basically 52% of the cloud users, they have ever experienced the personal data stolen. And also, the number of people willing to share their personal data fell from 41% to 31%, during the year of 2020. So because of all these kind of reasons, in our approach, we are trying to picture a scenario that people are more willing to share their personal data for collaborative training in a neighborhood. For neighborhood concept here, we are considering like more in a geography like perspective, and also the network relations all in one neighborhood. And the reason for our purpose to develop the previous system is because it's more privacy preserved and communication efficient and cloud service free. And here are some main contribution from our framework. So the first one, we developed a decentralized fairy learning framework, which is cloud service free. And since everything are kept inside one neighborhood, so we think that is more privacy preserved compared to sending either your personal data or gradients into the cloud. That will be much less controllable. And the second thing is we have a gradient selection mechanism. So because we are kind of in our framework, the gradient is going to be broadcasted from through different agents. So there will be a communication overhead, and we developed this gradient selection mechanism to reduce that. And also, in a way, it's kind of doing a personalization. We're gonna discuss that in the later slides. And in our paper, because there are a lot of IoT applications, right? So in this paper, we focus on a case study on residential building load forecasting. So why we choose energy load forecasting in our experiment? So basically, it's because it's pretty important among all IoT applications. Because like 39% of total energy is consumed by homes and all office buildings, and nearly 20% of the consumed energy are wasted. So that is a huge amount. And to save the energy and monetary costs from all these kind of waste energies, people are doing energy management systems. And in order to do that, you have to have accurate load forecasting as your first step. So we think this application is kind of meaningful for our framework. And also our framework can be used in other applications as well. And that's gonna be one of our future works. So first we discuss the decentralized fire learning framework. So the first step is we consider a residential building area with multiple residents in the system, and each residence, they have their own devices such as say TV, smart lights, or PC, or HVAC system, and all of them have a default machine learning model. In our experiment, we choose the long short-term memory for load forecasting. And the first step will be all the users for all the devices, they're gonna do localized training process, and the gradient is gonna be capitalized locally. And the second step will be all the, so in the first iteration, all the gradients gonna be broadcasted through different agents. So after step 2, all the smart agents have the gradients from all the other users. And in the second let me just first the first iteration then. So in the first iteration, all the gradients gonna be aggregated from the agent. And in the second iteration, since all the users have already have the previous gradients from others, so we can provide the gradient selection mechanisms. We're gonna introduce that in the next slides. So the purpose is to make it more communication efficient. And then after the gradient selection, the model gonna be updated, and so all the users gonna do the localized load forecasting by themselves with the update model. And for the gradient selection mechanism, so how we gonna do that? So there are like 2 parameters that we set during this step. So the first one is the gradient threshold. We determine that as alpha. So after the first iteration, we have all the gradients, right? So in the second iteration, we determine this threshold. And first, if the gradient of the certain device is larger or equal to the top alpha of the total gradients, will be selected as aggregate gradients, and it will be broadcasted for the next iteration. And if the gradients of the certain device is smaller than the top alpha of the total gradients, it will be kept locally and will not be broadcasted. And during the localized model aggregation, it will be added for that specific local devices. And the second parameter is the broadcasting rate, because we definitely don't want to like broadcast all the gradients like more frequently, because that will be like more communication is sensitive. So we determine this kind of parameter through our experiment to decide the best broadcasting rate. And our evaluation, for our evaluation part, the data set we choose is the biggest rate data set. So it is a real world data set, have say, I think it's a 1600 residence kind of data, and it contains all kinds of devices, HVAC, dryer, lights. And in our experiment, to determine the accuracy, we randomly select 100 residents for for our kind of perspective. We also have different number of residents joining in our system to determine the robustness. That will be introduced in the later slides. And for the model, the localized model, we choose long short-term memory. And we also have 3 compared methods. So the first one is smart energy management and demand reduction. So in this paper, they studied the usage behavior of consumers from their historical data and predict the demand for energy every hour for individual consumers using seasonal ARMA. And the second one we choose is the cloud forecasting system for monitoring and alerting. So for this paper, they propose a efficient cloud-based energy information management system for home appliance, and the method they developed is a kind of a combination for statistical methods and machine learning. The name is too long, so yeah. So and the third one is forecasting multi-appliance usage and energy management. So in this paper, they developed a graph neural network to do this kind of load forecasting and energy management system. So for the comparison methods, the 1 and 3, they are mostly focusing on one individual users. And for the cloud forecasting system, they kind of doing the collaborative training. And in our we also added like a pure traditional fairy learning methods as one of the baselines. So it will be better like show the performance of our proposed system. And as I said, we also have like different number of residents and different like training days to test the performance of our system. So the first one is the parameters that we discussed in the gradient selection. The first one is the threshold. So as we can see, we select different different thresholds, and the axis is the percentage of the gradient, and the y-axis is the accuracy. We can see that when we choose the threshold as a 50% or 60%, the accuracy is going to be higher than the others. And to achieve a good trade-off between the communication efficiency and the accuracy, we choose the alpha to be 0.5. And for the broadcast frequency beta, we choose that as 1. So for 1, basically is 1 hour. For each hour, we're gonna broadcast the gradient. And move to the performance. So the first, the matrix is the CDF for load forecasting accuracy. As we can see that our previous framework and the CFS, which is the cloud-based system, they kind of have the same accuracy level. And the ACM and FMA, they are kind of lower because most of them are doing the individual level of the load forecasting. And the figure on the right, basically what we are showing is the different time in 1 day versus the accuracy. As we can see that in the midnight time and also in the kind of afternoon time, the accuracy is going to be a little bit better than the noon and the evening time. So basically it's because in this experiment, we are considering like 100 residents, and they kind of have a different user pattern. And the energy usage during noon time and evening time going to be a little bit more difficult to predict, and that is also one of the reasons that one of our future work going to be personalization. So the accuracy going to be much more higher for that. And the third and fourth metrics that we want to show is the kind of like the system running days versus the accuracy. From the left side, we can see that the accuracy is moving, is getting better through the time, and it goes like steady, more steady at say kind of 2 months of time. So after that, the accuracy will not be like changed dramatically. And on the right side, we have the number of residents versus the accuracy. So as we can see, one of the interesting point is that when we are doing like more than 100 participants, the accuracy going to be lower for the other comparison methods. Basically, it's because they didn't do any personalization, and when we are adding more and more participants, the different user patterns going to be like make the model like less accurate. And because we are doing the gradient selection, so the accuracy is going to be a little bit more steady. But for this one, when we are applying say 300 participants, our model's accuracy going to be dropped too. But we didn't include that in the figure. And also one of the performance is compare our methods with the traditional fairy learning. So as we can see, the through the running days, the accuracy going to be like at the same level, and for different number of residents, that's going to be the same reason for the previous figure. And we also compare the communication efficiency. So basically, what we determine is the speed up percentage versus different number of running days and the number of residents. And we can see that our system going to be speed up comparing to the if we don't do the gradient selection. And move to the conclusion part. So basically, we propose the previous a privacy preserved communication efficient and called search-free fairy learning system. And our application right now most focusing on the residential building. And we also propose the gradient selection. And our system can have the nearly 97% on real world low energy data for load forecasting, which is as good as using cloud service. Yeah, so thank you. And yeah, so I'm happy to take any questions.
Thank you. Just check any question from the conference room. Okay, so if not, I have a quick question. So I just want to double check if it sets like the threshold alpha equal to 1, is that equivalent to the normal?
10%.
So sorry, I mean, if alpha equal to 1, is that equivalent to the normal further learning? So basically share every gradient you have.
Right.
So then do you have any kind of insight from your side why you do the gradient selection and also improve the accuracy? But because intuitively, so if you share more accuracy, if you share the gradient more frequently, you will get better information share among each other, which can potentially help you to improve the final accuracy. But turns out it's pretty interesting. We reduce the network load by randomly select the gradient. It can also help you to improve the accuracy. Do you think this is a kind of phenomenon only fit for the type of data set you're looking at, or do you think you have a kind of insight to say that this can potentially applied to other fuzzy learning algorithm as well?
Yeah. So so I'm actually have the same kind of question. So right now we only applied the energy data. So I cannot really say that if that is based on the data set. But one of our future work is to apply this kind of model into other applications, or which means the other data sets. So in that case, I can better identify if it's the data set problem or it is the fair learning framework thing.
Okay, sounds interesting. Looking forward to that.
Thanks. Yeah.
Okay, I think since that's all things have been finished, that's all our technical session. So officially, this is the end of our kind of workshop. Thanks for all the contribution, all your help, especially for helping to set up the Zoom. Yeah, I think that's the end. So hopefully we can see like not virtually, but in the same room next year in the AIoT workshop. Okay, that's the end of the workshop. See you next year. Bye.